What's up, everyone? Welcome to the CHEM 2323 final exam review. So I was not planning on making this video because I genuinely thought y'all had it in the bag at this point. But after seeing how cooked every single one of you is, including you watching this video, I had no other choice. I was quite literally forced to make this video. Now, some of you know, and most of you don't know, but this is my second time recording this video. And I was up at 7 a.m., okay, recording for 3 to 4 hours minimum. And it turned out I received a phone call, a spam phone call, despite being on airplane mode, despite my Wi-Fi being off. I received that phone call and I just laughed it off. I was like, oh, this is random as hell. You know what it did? It deleted the entire video. It didn't even let the video save. It just straight up killed it, murdered it, said goodbye. And I kept recording thinking like, oh, you know, this video is still there. No, I finished after 4 hours. I look back at my camera roll, boom, nothing there. It's like it never existed. And so I'm here recording this because I really, like, you know, I need you all to like learn. Like a lot of you are cooked, like genuinely. I'm not trying to be mean, but like, I will help you, okay? I will help you. Hopefully you're watching this video right now, meaning the day that is posted, right? So it should be a Tuesday. Wednesday is also fine. Thursday is really cutting it close. If you're watching this on Friday, it's not gonna be as helpful because I'm going to tell you how to do all of these reactions, okay? I'm gonna tell you how to study this. And here's a list of stuff we're gonna do today, 1 through 8. 1 through 8 is all your new things. So chapters 8, 9, and 10. This video is called an exam review for your final, which is comprehensive. But I'm focusing on the new stuff because exam 2 stuff, which is chlorination, SN2, SN1, that has its own video, which was posted like when you had your second exam. And if you need to watch that, you can just scroll in my channel and you'll find it there. As far as exam 1 goes, I don't have a video on it, but it's also fundamental things. I don't expect you to remember everything like I don't know, like Fisher projections and Newman and cyclohexane chairs. But if you at least encounter a question and get it wrong, you should at least, you should know how to fix it and how to get these things right. It shouldn't be brand new information. I shouldn't have to explain everything. And if you really need help, you can always find a different video on it. But if you look at number 9 and 10, I do have a couple things that I did want to talk about from exam 1 that I personally found confusing at the time when I was a student. But as far as everything else, ask a friend or ask somebody if you have the time, and you can get help from that. So the first thing we're going to talk about is strategies. Do not skip this, okay? Unless you have every reaction down, do not skip this. Because if you don't learn or strategize how to remember all these reactions, you're cooked for OChem 2. Forget OChem 1, you're cooked for OChem 2. Because OChem 2 is this, but worse. Especially the second half. It's like this, but worse. And of course, I always say that if you understand what's going on, it makes it easier. But I was a student, I didn't understand shit. I memorized. And a lot of you are gonna memorize too. And you gotta know how to memorize these. So I'm gonna tell you stuff, okay? My own students, I told them this, the session after their exam. Most of them did not listen. And a couple of them laughed at me when I told them these strategies. And those same students, one of them just told me the other day, OChem used to be fun, now it's difficult. Bro, I wonder why. You not listen to my strategies. So it's up to you. You might already have your own strategy. You might have these reactions down. But if you don't, this is especially for you. Do not disregard what I'm saying. Don't ignore it. Just listen, okay? I was a student. I wasn't the smartest student, like when it came to OChem. I didn't know anything that I know now. But I found a way to get through it. So I'm gonna teach you the strategies. And as you might be able to tell, right, via the strategies, you're going to learn the reactions. What is the purpose of this video then? If you're able to just look at the reaction sheet that I'm gonna tell you about. The purpose of this video is to explain how a lot of these reactions occur. I am not going to be covering every single reaction, but I will be covering a very high percentage of them. Because if you understand how something works, along with knowing what the products are, it will make it much easier to recognize it on your exam. Also, I know it's easier to learn from somebody explaining it to you rather than figuring it out on your own through reading. And one more thing, mechanisms are not the most important thing on your exam. They just care about, do you know the product or not? But when it comes to finals, they actually historically do ask 1 or 2 mechanisms. They'll give you a bunch of reactions, right? And then out of nowhere, there'll be a question that's like, can you draw the intermediate of this reaction? Or what is the intermediate of this reaction? Or what is the mechanism? How does it work from the very beginning to the very end? So I'm going to tell you a lot of mechanisms, so that you can hopefully be able to do it on your exam. And there will be some things, I'm telling you right now, there will be some things I tell you that are not important to know or most likely will not show up. And at that point, you can decide if you want to learn it or just not. But a lot of things I will tell you will be important to know. So it's up to you what you want to do with this video, okay? So the first thing, okay, strategies in terms of this, as you can see right here by this image, this is an example of what I did. It's just like a small version. But the step one, okay, look at your old slides and make a master sheet. Make a master sheet with every single reaction that you see and include notes and include all the reactions they give you. Like some of them, they'll only show you one example. Some of them, they'll show you two examples. Some will be three, right? Include every single one of them. And write notes. As you can see, if something's anti-Markovnikov, write that out. If something is rearrangeable, something can't rearrange, write it out. Write out all of these, make a master sheet for every single reaction. This should not be difficult because you're just copying and pasting. It should not be that difficult. I don't know why people don't do it. If you don't do it, you're just being lazy because it's very easy to do. And so make a master sheet and, you know, I might include my master sheets in the description of this video, but don't use them, okay? Do not use them. You can use them as reference to see how I set mine up, but don't use it, okay? Don't even use what peer tutoring gave you or what your professor gave you. Don't use those because I want you to make your own master sheet. I want you to practice writing out every single reaction. And one more thing, my master sheet low-key has some errors. So I'm not even gonna tell you what the errors are. So you don't use it because you don't know what the error is, okay? So that's step one. After you make your master sheet for every single chapter, do old practice exams and quizzes. So this can be from your professor or it can be through the Dropbox, right? So your professor will give you some, but there's also like a couple of Dropboxes. If you don't have the Dropbox at this point, I don't know why you don't have it. Be more social, okay? Ask students. I don't know, go into your group meet, ask for the Dropbox, ask a friend, somebody most likely has it. So, and okay, if you really can't find it, just like ask me in the comments, I'll give you, hopefully, I don't know. But that's what you're gonna do, okay? But when you do these exams and quizzes, you're going to cheat on them, okay? You're gonna use your cheat sheet because you don't know the reactions right now. You can't remember anything. So if they give you a question and they ask you, what does this give you? Right now, you don't know it, right? I'm just assuming you don't know. You might know. I'm just giving an example. You don't know. That's okay. You don't have to know. Look at your cheat sheet, see what the answer is, write your product, okay? Continue for the next one. Whatever else they give you, do that. Then after you do it, you'll hopefully be more familiarized with a lot of the reactions and then do it again, right? Step 3 is do them again. Do as much as you can, right? Do them all over again. And this time, do it from memory. So you might be thinking, what is the point of this? Like, I'm just gonna memorize the answers. Yeah, that's what you want. You want to memorize the answers. Because if you memorize what the product is of a reaction, you'll kind of understand how it works. So if it shows up a little bit differently, you'll understand. So that's what you're gonna do. Make a master sheet, do old exams and quizzes with your cheat sheet, and ultimately don't use your cheat sheet and have them memorized. Knowing your reaction is very important because I am going to, like towards the end, I will be talking about synthesis and like how to approach them. But there's no point learning how I do synthesis if you don't know that a reaction can occur. For example, this is obvious to me, right? I know that there's no such reaction in one reagent that can attach a carbon here. I know that because I know all the reactions that are available. But you or someone who doesn't know what's going on might not know. So you might look for a reagent that does this in one step. If somebody knows the reactions available, they'll know, oh, okay, I can't do this, but what I know how to do is form a double bond or attach a bromine, form a double bond, continue this on somehow, right? If you know what's available, you're able to logic things out. Even if you don't remember the reagents, at least knowing that something is possible makes a big difference. Otherwise, you're not gonna know anything and you're gonna be completely stuck. One more thing, right? I'll give you another example. This is like something that everyone should know. If I'm trying to add something here, right? Like let's say my product looks like this and I have a bromine here. You can't do this. This is not like a one-step thing. At least it's not a major product. But what you know how to do is double bond to that, And you know how to make a double bond from the alkane and all that stuff, right? That's what I'm saying. So really get familiarized with your reactions and don't make the excuse that you have other exams to worry about. It doesn't matter, okay? That class you can make the same excuse for. I have OChem to worry about. Make sure you prioritize this and hopefully everything will work out, okay? Now, enough of this. We're gonna start with nomenclature. So nomenclature of alkenes, alkynes, and alcohols. It's very similar to alkanes. Let me give you this. So the first thing to keep in mind, you want to have your numbering such that it's the longest continuous chain that contains your double bond. So in this case, my longest continuous chain will be this. Now, how do I number it? I number it so that my double bond gets the lowest numbering because my double bond has the highest priority. In a case like this, right, there's no priority between chlorine and fluorine. It doesn't, like, you don't have to have chlorine as the lowest possible or the fluorine as the lowest possible compared to the chlorine. In this case, it doesn't matter. Fluorine's not better than chlorine. So you just number it such that everything has the lowest numbering. But in this right here, right, in this, even if my substituent, let's just draw another one. If I have a substituent at the very end, like that, I don't care. I'm going to number it this way, right to left, even though my fluorine and chlorine will have very high numbers, because my priority is this. Whenever you have priority, you're literally prioritizing it. So you're going to give it the best number. So I'm going to number this as usual, 1, 2, 3, 4, 5, 6, and 7. And this is a hept, right? But it's an alkene with a double bond, so it's a heptene. And what do we have? We have a 5-methyl, we have a 6-chloro, and a 4-fluoro, right? 7-fluoro. This is all like exact same as you would do with an alkane. Now, the ultimate thing to do is mark where your double bond is. Yes, this is a heptene, but so is this, so is this, so is that. So you gotta mark where your double bond is. And our double bond is between carbons 2 and 3. You take the lesser of those two values. So you're gonna call this a 2-heptene. Or the better way to do it is hept2-ene. I will show you why this is the better way in a little bit. But let's put it all together. 6-chloro, right now you alphabetize them. 6-chloro, 7-fluoro, 5-methyl, hept2-ene. Okay, if I had a triple bond, pretend this is linear, but if I had a triple bond, it would just be hept2-ine. Okay, what if I had this molecule right here? This is a butene, but there's 2 alkenes. So instead of butene, it's a butadiene, and it's on carbons 1 and 3. Buta-1,3-diene. If I had 3 double bonds, but-triene, or whatever the case is. That's actually not possible, but you know, hexatriene or something. Same with alkynes, hexaine, hexatriene or something. Now, what about alcohols? Same thing with alcohols, okay? You're going to include the chain, the longest continuous chain that includes this alcohol, and you're going to number it such that your alcohol has the lowest value. So same thing over here. Even if I have this chain and I have fluorine here, another chlorine, bromine, I have 3 substituents where if I number it left to right, they're all going to be very high number. Or if I go right to left, they'll be lower and my alcohol will also be like lower, right? I don't care. I'm going to number it so that this gets the lowest numbering. So I'm gonna go left to right. So 1, 2, 3, 4, 5, and 6. Okay. This is a hexane. What do we have? 3-methyl, 6-fluoro, 6-chloro, 6-bromo. So what is this all together? 6-bromo, 6-chloro, 6-fluoro, 3-methyl. Okay, now this is where the alcohol comes in. What is it? It's a hexanol. Okay, it ends in hexanol, ends in ol, because it's an alcohol. So you mark where the alcohol is, hexan-2-ol, or you can say 2-hexanol. But once again, I'll show you why I like this version with the number in the middle. So it's hexan-2-ol, and think about it. It's called an alcohol. Alk refers to the alkane in all. So like hexanol, pentanol, butanol, decanol, nonanol, all that stuff. Now, this is the order of priority. Double bond is higher than anything else that's not a double bond. Like everything else that we learned, like fluorine, chlorine, methyl, alkyls. Double bond is better than those. But what's better than a double bond? Triple bond. And what's better than a triple bond? Alcohol, for now. These are your orders of priorities, right? Everything else. So what does that mean? Let's say I have this molecule right here. If I number it left to right, my values are going to be 1 and 5. If I number it right to left, I will have 2 and 6. 1 and 5 is obviously better than 2 and 6 as a whole, but since the alcohol takes priority over the double bond or even a triple bond, you number it such that your alcohol has the lowest numbering. So I'm gonna go right to left, right? It's either left to right, which is a 5, or right to left, which is a 2. So I'm gonna go right to left. 1, 2, 3, 4, 5, 6. So this is going to be called what? It's a hexenol, hexenol. So remember what I told you? If you put the number in front, how would you do it? 2-hexanol? Where's the carbon? Where is the double bond going to go? Or which one is the double bond? Which one is referring to the alcohol? You can't say 2,5-hexanol. That makes no sense. So you have to put it in the middle. So what you're going to do here is hex 5N2-ol. This is saying that my ene is on the 5 carbon and my ol is on the 2 carbon. That's why they do this. So that's what my product is, a hexenol or hexenol. Okay. One more thing. If you had 2 alcohols, so like that, what carbons? 2 and 4, and this is a 5 carbon molecule. So this is a pentan 2,4-diol, right? Di means 2 and the 2 alcohols. Pentan 2,4-diol. In this case, you can also do 2,4-pentane-diol. Now we get the idea. It's good, right? It's not that difficult. It's just like alkanes. It's just now you're introducing priorities and stuff. Let's move on to our actual alkene reactions. So, as I mentioned, I'm going to explain mechanisms, and I'll tell you what's important, what's not, or what's not as important, but might still be important. The first reaction we're gonna do is our HX. X refers to halogen, that's not fluorine. So this could be HCl, HBr, HI. These are all strong acids. When you have an alkene that looks like this, and you do one of those, let's just do HBr, that's a very common one. What is HBr actually? It's H plus and Br minus. So my double bond is electron rich, therefore it's going to try to form a bond with the hydrogen. Now I can either form a bond with carbon A or carbon B, right? I can use a double bond to form a bond with the H, and this could come from carbon A or carbon B. Well, which one does it? Take a look at what happens if you do carbon B. Let's do carbon B first. Carbon B formed the bond, right? So using this double bond from carbon B, therefore, when you have your hydrogen here, carbon A is lacking. It's lacking a bond. What does it have right now? It has 2 hydrogens and it has this double bond. That's 4 bonds. But since you're using that double bond from carbon B, what does it have? 2 H's and a single bond. It's lacking a bond. Therefore, this is going to be carbocation on the primary. Okay, if you say carbon A steals the hydrogen, what is your intermediate? Intermediate is this. Which one is better? Secondary is better than primary. So this is the one that's going to go through. However, pay attention to how it's a carbocation. Carbocations can rearrange, and that's exactly what's going to happen if it's going to end up in a better position. You can do a hydride shift right here, right? So you're going to end up with a tertiary carbocation. That's your true intermediate. And what are you left with now? You still have a Br minus. The Br minus will attach itself there, and your ultimate product will look like that. That's what HX addition is. Now, some people refer to this as Markovnikov. I mean, yes, you can call it that. We'll just make that note. It's Markovnikov, but it can also go a step further. It can rearrange. Usually Markovnikov refers to like the more substituted of the alkene carbons. So in this case, B versus A. But since you can rearrange, I don't really consider that Markovnikov, but it's okay. As long as you remember it the right way, you're fine. This is a Markovnikov that can rearrange. Just remember this. And don't forget the rearrangeability rules. We have H shift, a hydride shift, a methyl shift, and a ring expansion. I believe ring expansion is covered in my OChem exam 2 video, so if you need help with that, just watch that. But you're not, I mean, I wouldn't say not likely to see it. Who knows? Who knows what they throw at you? But remember H and methyl shift. So if I had this right here, and I reacted with hydrogen and iodine, right? Hydroiodic acid. What is my intermediate? Looks like that. And I can methyl shift. So I'm going to make it this. And my iodide ion will come there, attach itself, and become that. That's my product. So we get this now, we understand. But since there's a Markovnikov, there has to be an anti-Markovnikov. Otherwise, what the hell is going on? So now we're gonna do HX with Ruhr. What is Ruhr, okay? We write Ruhr a lot, but make sure you recognize it. All it is some R carbon chain bonded to an oxygen, which is single bonded to an oxygen, bonded to another R chain. So I can have CH3, oxygen, oxygen, CH3, or I can have H2O2, which just looks like this, right? These are all called peroxides. Now, the thing about peroxides is that oxygen single bonds are very weak. Therefore, these are very likely to just become radicals and break themselves apart. So that's exactly what's gonna happen. Let's say I have a reaction here that looks like that, and I'm reacting with HBr Ruhr, okay? Literally what's gonna happen is it's gonna homolytically cleave. And what do you form? Radical oxygen. Now radical oxygen will encounter HBr, and radicals react with everything they want to. They react so much. This is just like your initiation, propagation, termination. This is initiation phase, by the way. It's very similar to your monobromination. So you form this radical, it's going to steal the hydrogen from the HBr, and in turn, you're gonna form an alcohol, of course, but you also have a bromine radical, okay? So if you have a bromine radical, which encounters this alkene, same deal here, right? You're gonna decide which double bond carbon does it react with. If I say it bonds here, and this goes towards that bond and this one breaks off, my radical would be on this carbon. So what does that intermediate look like? I'll have a bromine here, and I'll have a radical on the secondary position. If I do this carbon, if I bond to that carbon, so let's erase this. Wrong one, sorry. If I say my bromine radical bonds over here, it's gonna bond here, right? You use one of the electrons to form that bond. The other one will go as a radical. What does that intermediate look like? It's gonna look like this. My bromine on the 2 position and my radical on the primary. So this is my intermediate, right? I don't care about my product. I care about the intermediate. The intermediate judges, it dictates how the reaction will proceed. Do not look at products, okay? Big misconception, don't look at products. You're looking at the intermediate, because that's the rate determining step. And which is more stable, a primary radical or a secondary radical? Radicals are just like carbocations for ranking, because they're both electron deficient. So we know for carbocations that more substitution is better. So that means that for radicals, more substituents is better. And so this is the one that occurs, right? That's going to be our actual intermediate. So we're going to scrap this. Now, since this is our intermediate, what ends up happening? You encounter another HBr. And I said radicals react with whatever they want to. So this radical will react with the hydrogen, and the hydrogen will form a bond. Well, this is poorly drawn, but you guys get what I'm saying. You're forming the bond with that carbon, and you're breaking off this bond to the bromine. So you ultimately end up with a product that looks like this. And what happened over here? I just formed more bromine radicals. And what is a bromine radical gonna do? It's gonna keep reacting with whatever it encounters. This is the propagation phase. You don't have to know this, but I'm just drawing the similarities between this and the monobromination that you learn, right? So our ultimate product ends up being this. Our bromine is on the less substituted carbon because our intermediate was a radical that was on the more substituted carbon. So this is called anti-Markovnikov. This is a true anti-Markovnikov, because out of these two carbons, you're on the less substituted. In terms of the bromine is on the less substituted carbon. So that's how that works. Now let's do another type of reaction. A lot of these reactions, at least for alkenes, work very similarly. So the next one we're going to do is, it's straight up called hydration. All right, hydration. The reagent here is H plus H2O. This can also be written as H3O plus, right? I'm just exposing you to different methods of drawing these. But H plus H2O, H3O plus, same thing. It's called acidic water, right? Emphasis on acidic. It's the same thing as your HX, right? What was HX? It's literally H plus and X minus. Your X minus was a nucleophile. Your H plus just bonded to one of the carbons. Over here, your H plus just bonds to one of the carbons, and your H2O is a nucleophile. So how does this work? You know how it works, okay? Which carbon A or carbon B, will the H plus be bonded to? We know it's going to be carbon B. We know that this carbon will bond to the H, because what is our intermediate going to look like? Our intermediate will look like this: secondary carbocation. And as you can see, we can rearrange it 1 over via a methyl shift. So what do we get? That. And then ultimately, you have an H2O come in, weak nucleophile, but it's still a nucleophile. This will attach itself. And technically what you get is that it's just a water attached. But remember, like, you can assume a workup step happens. So you can remove a hydrogen and just keep it as an alcohol. So you'll end up like this. But in reality, you had a whole like water molecule attached. But, you know, H plus H2O, HBr, HCl, HI, they're all the same thing. Okay? Now you're probably wondering, okay, if I can rearrange how to do Markovnikov, how to do anti-Markovnikov alcohols, oh yeah, there are reactions for that. And you know them actually. Some of you should know them. And I'm gonna bring this reaction up again when I talk about those, which actually will be coming very soon. But first, before we move on, we're going to talk about how do you make alkenes. I should have started with this, but I just forgot. But the next reaction is making an alkene. There's several ways to do this, but the one I'm going to mention at this exact moment is something that you should know. It was on your last exam, but people forget it. What am I talking about? This. An alcohol reacting with H2SO4 or sometimes H3PO4. Ultimately, you form a double bond, but this is an E1 reaction. How does this work? H2SO4 makes sense. H3PO4, I don't get why they use it, because H2SO4 is a strong acid. H3PO4 is not, but I've seen both of them, okay? So when you have H2SO4, this is a strong acid, meaning it has a proton, and the other part's a weak base. So you're gonna protonate this alcohol, and I wouldn't really call it, it is one of the intermediates, but it's not the rate determining intermediate. What do you have? You have a leaving group. You have a leaving group right here. It's a water that's attached to a carbon. Now, this guy, it's a weak base. That's why we're gonna do E1. It's here, okay? But I said it's E1 because it's a weak base. So what is the first step of E1 or even SN1? Leaving group leaves. So this is your real rate determining intermediate. Carbocation. What can carbocation do? It can rearrange. So it's going to shift over to the tertiary position. Okay, now your HSO4 comes in and it will take one of these hydrogens, right? You have this option, and that option. Obviously, we're gonna do this carbon's hydrogen because when you steal that hydrogen, you're able to form a Zaitsev product, right? So you steal this hydrogen, form a double bond, and you ultimately end up with that as your product, right? It's tetra-substituted, the most stable alkene you can get in this case. What else can we do to make alkenes? Just E, right? E2, E1. So if you have a molecule that looks like this and you want to form an alkene, just use like LDA or something, right? LDA is a bulky base, but in this case, it doesn't matter. You'll form a double bond, the same product. If you had a molecule that looked like this, and I wanted to form this alkene, I can use another strong base that's not bulky, like NaOH. Right, NaOH is my go-to when it comes to these things, and there's no fear about doing SN2 because this is tertiary. OH is a strong nucleophile, but this is tertiary, so you don't have to worry about SN2. Therefore, E2 will occur. Guys, don't forget this because this is fundamental stuff. But from what I've seen, like people are forgetting. If I need to go from an alkane, guys, pay the fuck attention. If I need to go from an alkane to an alkene, what is the first step? What is the only thing you can do with an alkane? You have to. The only thing you can do is brominate or chlorinate. So Br2HV is the only thing you know how to do on an alkane. You can't do any reaction if you don't have a leaving group. You can't form a double bond. You can't SN2. You can't E2. You can't do any of that if you don't have a leaving group. So alkane, anytime you see an alkane, the only thing you can do is form a leaving group. So that's what you're gonna do. So I'll form a leaving group, and then if I wanna make my alkene, then I can do an E1 or E2 reaction, and like I'll just do LDA for example, and that will give me my alkene. So don't forget this, okay? Don't forget this. One more time, emphasis on this reaction is an E1 reaction, okay? All right, let's move on. Let's get rid of all this. Now, if I have this, right, same damn molecule, there's three things I can do. I can make a product where the OH rearranged to a tertiary. I can make a true Markovnikov product, or I can do the anti-Markovnikov product. Right? These are all three different molecules. Three different things occurred. What are the reagents? We'll talk about it, and then we'll talk about like how it works. So the first one we already talked about. We already know this, right? If you want to form a carbocation that rearranges, just do a reaction with H+. So H+. And what am I trying to add in alcohol? So H+, H2O. I believe you can also do, no, never mind. I'm not going to tell you. H+ and H2O. That's what you're going to do. Now, what is this second one? This is going to be the reaction called oxymercuration, demercuration. I will explain this, but first let's write it out. HgOAC2, technically THF, and there's also like a, hold on. Let me write it out over here. THF, H2O. I'm gonna put this in asterisk, right? I'll tell you why. And step 2 is NaBH4. So essentially, step one is going to be, actually we'll talk about this in a little bit. We'll talk about this later. But this is what your product is going to be. It's called a Markovnikov alcohol addition, where your alcohol ends up being, out of these two carbons, the more substituted one. And if I wanted to add to the less substituted one, what do I do? Sorry guys, I think I was being snitched on by someone. That's why I was tripping. Yeah, I got snitched on. Bro, this guy's dumb as hell. Okay, forget that. If I want to do an anti-Markovnikov, I'm going to do this reagent. BH3, THF, H2O2, NaOH. Okay, so we have three methods of forming alcohols. You can rearrange, right? This is the rearrangeable one. This one is Markovnikov, and this one is anti-Markovnikov. God, it's so funny. I had a student who told me that anti-Markovnikov sounds evil, like anti-Einstein, like evil Einstein. This is evil Markovnikov reaction. That's what's happening here. But these are the methods, okay? Now let's jump into the second and the third one, right? We have oxymercuration, demercuration. Oxymercuration, demercuration. And sometimes it can be called alkoxymercuration, right? Alkoxymercuration, demercuration. Oxymercuration just means I'm adding an alcohol. Alkoxymercuration means I'm adding an alkoxy group, which is just OR instead of OH. So if I have this, and I'm reacting, the reagents once again are HgOAC2THF, in this case H2O, right, H2O. That's step one. Step 2 will be NaBH4, which you should recognize from another current reaction. if you're wondering what OAC is, AC just refers to acete, right? This is called like an acetate ion, and there's two of them. But what is your reaction look like? What is your intermediate? I would know this one, okay? This one, the intermediate, will look like this. This is I think it's called a merconium or mercuronium ion, something. So the Hg is bonded to OAC. If you're wondering what happened to the other OAC, I don't fucking know. It's just floating around like this. But nobody cares, right? Nobody cares. It's just there. So this is your intermediate. Do I have a true carbocation? No, I don't. The only cation is on the mercury, but on these carbons, there's no true carbocation. So what I do have is partial positives. Partial charges cannot rearrange, but I do have partial charges. And so the next thing is the H2O comes in, right? H2O. H2O is a weak nucleophile. And when we hear weak nucleophile, we think of SN1, more substituted carbon. That's what's gonna happen here, right? Between these two carbons, which one is more positive? Which one holds a positive charge better? It's the more substituted one, because more substituents means more electron donating effects, which means it's more stabilized. So the more substituted position will be the better place to attack, the better electrophile. And that's what's gonna happen. You're going to attack this carbon. And when you do that, you kick off that bond. And what do you have at this moment? So you added your water, and you now have your HgOAC right there. Okay? That's what step one was about. And by the way, I'm going to deprotonate this just to keep it simple. That's what step one is. What is step two? Step two is NaBH4. NaBH4 will ultimately remove this, okay? NaBH4 removes the mercury with the acetate to give you a final product of that. So the key pointers here, okay? You cannot rearrange because there is no true carbocation. As we saw over here, we just have partial positive and partial positive. We don't have an actual positive, we just have partials, so no rearrangement. Number two, NaBH4 is necessary, right? Don't disregard this in your reaction because NaBH4 literally removes the HgOAC. If you don't have NaBH4, this is your product right here, which is stupid. You don't want that. And the third thing, which I didn't mention, you have an anti-addition of alcohol and H, okay? Here's the thing. Wait, keep in mind, this is a Markov-Nikov reaction, but anti-addition of your alcohol and the hydrogen. What this means is that I guess it's not anti-addition of this thing, okay? Anti-addition of that in this. Here's why it doesn't matter. Because this carbon ends up never being chiral whenever you do this reaction. And so even if you want to show anti, like it doesn't matter because you have three of these here, or maybe you'll have two. So I would just know that it's an anti-reaction, but it ends up never showing up. Same with the other reaction we're going to do. So just keep this in mind. Okay, that was oxymercuration. If I wanted to do something other than an OH, I want to add like a OCH2CH3, I can do that. What am I gonna do? HgOAC2THF, okay, that stays the same. This time, what do I wanna add? Let's say I wanna add this right here. I'm gonna include that. I'm gonna include this alcohol. And then I'll do my, step two being NaBH4. Same exact thing. My intermediate is going to look like this. HgOAC plus. And now I have my alcohol come in. And this will attack, do whatever you think it's gonna do, right? And you're going to get your HgOAC. And now you have this thing attached. And of course, this will get removed. That's what I can do. What if I wanted to attach a alcohol over here? Or like an alkoxy group? I'm not even gonna tell you, you tell me. I mean, I'll tell you, but you know how to do it. I'm telling you, you know how to do it. What did we say allows for rearrangement if you have an H+? So that's what you can do. You can do an H+ reaction. You're gonna do H+, and what? Well, let's say you wanna add a methoxy group, just CH3OH. First step, form your carbocation. Second step, rearrange it. Third step, SN1, technically. And you get that. So we know how to do those. Now the final thing in terms of adding an alcohol or an alkoxy group is going to be the anti-Markovnikov version, right? The BH3THF thing. So this one, it's called, I think it's called like hydroboration oxidation or something. I'll just write it out. Hydroboration oxidation. The reagent, let's do the thing. So the reagent is written above, but BH3THF peroxide and strong base. Do not ask me the mechanism for this. It's chaotic, at least the way I learned it. So I'm not going to do it. I'm just going to give you the product. The product is what we have left, the anti-Markovnikov addition of alcohol. Now for this one, it's supposed to be a syn addition of OH, and I believe it's either the BH3 or the H. I don't really know, but it doesn't matter because you always end up having something that's not chiral. So like this ends up being achiral. This is also achiral. So it doesn't really matter. You don't have to show it because you can just rotate and get this product. So don't worry about the little note I said, just know the product. Now you're wondering, how can I add an alcohol? Well, I mean, I add an alcohol at the end, but how can I add an alkoxy group there? Like what if I wanted this product? I don't believe you can alter this to do that. So I will tell you what you can do using the reactions we know at this point. We can do this, okay? HBr peroxide. That will give me a bromine here, okay? How do I go from this to that? Or no, not that, we don't want that. How do I go from this to that? This is your nucleophile. Just make it like, you can do strong nucleophile here, right? So do that in Na. This is just SN2 because I have this negative attacking that carbon, kicking this off, and that gives me this product. So now we know how to add alcohols as well as alkoxy groups by rearrangement. So this one, we know how to do it Markovnikov and anti-Markovnikov. These are very important reactions to know, okay? So if you need to rewatch this part, rewatch it. It's tough, it's important. Alrighty, let's move on. The next set of reactions we're going to do is called, I think it's just called halogenation. Don't mix this up with monohalogenation. This is just called halogenation. The reaction will look like this. You have an alkene, and you're reacting with Br2. And sometimes, okay, in my notes, I wrote it like this, CCl4. CCl4 is a solvent. So Br2 in carbon tetrachloride, I don't know if you need to write this, but if you see it, if they give you a reaction that looks like this, don't be scared and think, oh, what the hell is CCl4 gonna do? That's just a solvent. The main thing here is the Br2. This one, I would also like recommend knowing the mechanism. You have Br. The double bond is going to bond to one of the bromines and remove this one, kick it off. What carbon does it? It's actually both of them. Your intermediate will look like this. This is called a bromonium ion. Stupid, right? Bromine is usually negative, but this one's positive. So you have a bromonium ion. Give me 1 second, let me redraw this. Bromonium ion, and then you have a Br minus floating around. In order to neutralize charges, what do you expect to happen? The bromine is going to attack one of the carbons. As far as which one it attacks, it doesn't matter because if I attack this carbon, what am I gonna do? I'm gonna kick this bond up and the bromine will go to this carbon. If I attack the other carbon, if I attack this carbon, what's gonna happen? Remove the bond and now this carbon has a bromine, right? Both of them will get the bromine regardless. So it doesn't matter, but if we logic it out, if we logic this out, it makes more sense that we attack this carbon because it's less sterically hindered. This is a strong nucleophile. I'm personally logicking this out. I might be completely wrong, but it doesn't matter here, right? Perfectly fine for me to be wrong because it doesn't matter here. It's gonna give you the same result. So we'll just say we attack this and this bond has to break. What is your product going to be? So this one, I need to specify something. This is anti-addition of two bromines. I drew it here, this one going up and this one going straight down. That shows anti, but if you wanna make it like more obvious, you can also use dashes and wedges, right? So we'll do a wedge bromine and a dash bromine. Of course, this carbon is not chiral, but we'll make it chiral. We'll make it chiral just for you, okay? We made it chiral. Both of these carbons are chiral. Now it matters, right? So I'm gonna put my hydrogen on a wedge. This is how you can show the product. You can also show the product as I did initially, where I have one bromine going up and the other one going down. And then the other ones, you can just figure that out, it doesn't matter. But you wanna make sure, I guess, that it looks how it was to begin with. So let me give you another example. Let me see if I can give you a better. I might actually draw the same one, but let me just, give me 1 second. So we have that, and we'll do this. Okay, if I react, I don't know. Okay, if I react with Br2, my product will look like this. So I'm gonna keep my methyl down there in my isopropyl like that. And then I'm going to do a wedge bromine here and a wedge bromine here. No, sorry, what am I doing? A wedge bromine there and a dash to show that they're anti. And then these two things were anti to each other initially, so they should be anti to each other ultimately. So that means my dash over here can be my ethyl, and over here my wedge can be my ethyl. So this is what I'm referring to. Your product should maintain the stereochemistry of the initial molecule. So once again, the bromines are anti to each other. You can show either by line, two lines going opposite directions, or just wedge dash. The things in the alkene that were anti to each other should also be anti. So this isopropyl and this methyl were anti. So we show that here. One's going up and one's going down. Our ethyls, right? These two ethyls were anti to each other. So these should also be opposite directions, indicated by the dash and the wedge. Right? What is a wedge and a dash? Wedge and a dash, wedge is pointing towards you, dash is away. But it's in the same plane. So they're anti to each other, 180 degrees. Okay. Let's continue this, but we're gonna do a little bit of a different reaction, but it's very similar actually, it's very similar. It involves Br2 again. The next reaction is called a halohydrin. Halohydrin. Halo refers to halogen and hydrin refers to water, hydro, right? So this reaction can look like this. Br2H2O. This time the H2O is not a solvent. It's not like CCl4. This is actually part of the reaction. What is your intermediate? Your intermediate is the same thing. It's the bromonium cation. And this time you have an H2O, right? H2O is in play. Now, what is the H2O going to do? Where do you think it's going to attack? Well, just think about it, right? We have a, what's it called? We have a partial positive here and a partial positive there. H2O is weak nucleophile. Okay, so we have a weak nucleophile and this one's more partial positive, so we're gonna attack that. So I'm gonna attack this, break off the bromine. I'll still have an anti-addition, so I'm gonna have, hold up. I hate this stupid example. So I'm gonna have my OH here and my bromine on a dash, and then I'll keep my ethyl there. So remember, it's anti because we're doing a backside attack. Just think about it. If I had a bromine, like this big ass complex in front of me, and I'm trying to attack it, I can't attack from the front because the bromine and all that stuff is in the way, so I have to attack it from the back. So even though I said it acts like SN1, it's weak, right? I'm just using these terminologies to like explain a little bit of how it's working, but it's not exactly an SN1 style reaction because you're doing a backside attack and you're leaving yourself with anti-products. But it's SN1 in the sense that you attack the more substituted and you have a weak nucleophile. So that's what this is gonna look like. Now you're probably wondering, where the hell is the other bromine? God knows. Just kidding, I know. So H2O, this is irrelevant information. This is just if you're wondering. It's going to be solvated. So like your water molecules in the solution are just going to stabilize it, right? Through like H bonding or some bullshit like that. And your bromine is just chilling. So this will just be in the background. If you're wondering what happens to the bromine, that's why the water attacks. Because your bromine minus the bromine anion is stabilized And so ultimately your water is free to react, whereas your bromide is not free to react. That's why you get this product. That's why you get a halohydrin and not just like a dibromide. Alrighty. Let's move on. So this next one is a fun reaction. I think all of these reactions are fun, but this one is fun. It's really easy, okay? You should know this one pretty well. If I have this and I'm reacting, this is called hydrogenation or hydrogenation. H2 and either PT, PD, or Ni. Okay, make sure you use these. I had a student who used lead and they got it completely wrong. So platinum, palladium, or nickel. Your product will be this, right? Where you attach two hydrogens in a syn manner. Of course, this is not a chiral molecule, but I'm just showing you that the two hydrogens that got added are syn to each other. So that's the only difficult thing. Just remembering that's a syn addition of hydrogens. And that's easy. If you're wondering how this works, okay, you do not need to know this. I'm telling you, you do not need to know this because this is a conceptual thing. It's not really a mechanism. You have H2, right? H2 is very stable because it's a diatomic gas, neutral. So you need a catalyst. You need a catalyst like this platinum. The platinum will essentially, it's a catalyst, so it's gonna break up the bonds. As far as if you become radicals or plus and minus, I don't know, bro. But you're gonna break them up. And both of these are going to attach to either carbon. And they're coming from the same side. They're coming from the same side, therefore it's a syn addition because they're coming from the same side, right? That's what syn is. So that's how it works if you're wondering. But let's do a question where chirality matters. If I had this, and I wanted to do H2, sometimes you'll see PDC, it's the same thing, okay, it's another catalyst. Your product will be this. My two substituents should be syn to each other because you don't have to write this, right? You don't have to write this, but my two hydrogens are syn. So therefore my other things will also be syn to each other. That's what you gotta know about this reaction. All right, moving on. As I told you, I'm skipping some reactions. Okay, I'm skipping some reactions. So if I'm skipping something, it's your job to figure it out because I'm not covering literally everything. I'm covering the stuff that's important, in my opinion. Next is going to be your peroxy acids. So you have all seen MCPBA and stuff like that, but what is a peroxy acid actually look like? You should be familiar with this formula. RCO3H, okay? Or RCOOOH. Or this. This is what a peroxy acid looks like. This is your CO3H part, and the carbon, right, this is just an R group. So we all tend to use MCPBA. We all tend to use we all use MCPBA. Now you're wondering, why did I write it in lowercase? Because this is the correct way. They teach you capital MCPBA. No, it's lowercase MCPBA. I'll tell you why. This is what MCPBA looks like. So this is called, okay, look, if you had this right here, this is extra information. If you're a tryhard, stay here. If you're not, skip this part. This is called a benzoic acid. It's a benzene with an oic acid, a carboxylic acid. So if you have a peroxy acid version of it, it's a peroxybenzoic acid. So instead of benzoic, it's peroxybenzoic. So that's this, right? The PBA part, peroxybenzoic acid. MC refers to metachloro. This is some OChem 2 stuff, but if you have a substituent over here, that's called ortho. If you have something over here, it's called meta. And if you have something over here, it's called para. This is ortho, this is meta. So your carbon on the meta position has the chlorine, right? Meta to this thing right here. Therefore, you call it a meta or just M-chloroperoxybenzoic acid. Meta-chloroperoxybenzoic acid, MCPBA. That's why they call it that. And that's why it's lowercase, because meta is a lowercase prefix thing. Okay, so let's do the short answer of what this makes. If you react it with any peroxy acid, the short answer is you form an epoxide ring, and they have to be on the same side. They have to be the same side because if you think about it, try to visualize this geometrically. This carbon, if it's bonded to an oxygen, this one has to also be bonded to the oxygen in the same direction. Because you're coming from the same molecule. So if I'm bonded from the front, how can I bond like from the back? It doesn't make sense. Or if I'm bonded from the back, how can I bond from the front? Doesn't make sense geometrically, so it has to be from the same side. So you can also have this right here, right? As long as you're on the same side, doesn't matter. Now, I'm gonna tell you something. You do not have to know this. I hope you don't. But I'm gonna teach you how does a peroxy acid thing form an epoxide. So we'll draw our peroxy acid like that. So double bonds are electron rich. So the double bond will form a bond with the oxygen. Okay, one of the carbons will form a bond. How do you form a bond over here? The oxygen will use its OH bond to bond here, okay? Now remember I said these bonds are very weak, they're gonna break. This will break and form a double bond, okay? And if I do that, I have to break a bond, right? This carbon has 1, 2, 3, 4. So I'm forming a fifth bond. What has to break? My pi bond. So this is going to break and attach to the hydrogen because my hydrogen is no longer bonded to the oxygen. The oxygen used the bond to the carbon. So what do I end up with? Same side bonding to the oxygen for my epoxide ring. And the other side, look what it became. Do you see how my purple carbon was single bonded and my red carbon was double bonded? I made a carboxylic acid, but now it's different. My red carbon is single bonded, it's an alcohol, and my purple carbon is double bonded to make the carbonyl part of the carboxylic acid. That is what is occurring here. But remember, as long as you form your ring, that's all that matters. Now, okay, guys, keep in mind, some of my video actually saved. I look back at my camera roll. So I'm gonna cut this recording at some point in the Alkyne reactions, but I don't remember what I said in what part of the video. So if I say something that repeats itself, that's just more emphasis for you, but don't think I'm an idiot. I just don't remember what I said where. But I want to tell you that's something that someone brought up to me. Like if you had this right here and you want the product, there's two possibilities, right? There's two possibilities. You can get that, or you can get this. Which one do you write? It doesn't matter, okay? If you look at some of your old exam keys, they'll write one of them and they'll put plus enantiomer. I know these are not enantiomers, but they're just referring to the enantiomer of this, so like the opposite. It doesn't matter. And you're probably wondering, okay, what about chair stability? Like what about if this has two equatorials, this has two axials, do I do this one, major product? No, major product has nothing to do with the stability of your product in these reactions because major product is dictated by the intermediates. So it doesn't matter, right? It doesn't matter which is more stable or less stable. You can write either of them, or if you want, you can write both of them, or you can write one and say plus enantiomer. It doesn't matter. Don't worry about if a product has like two ways of being written. You don't have to do them both, right? So you can either, for example, in our previous reaction where we had like this, you can do that, or you can do that, right? These are enantiomers of each other. It doesn't matter. It doesn't matter. Or technically, okay, forget it. These are not enantiomers. You're identical. But just pretend rest here. Let me just draw this here. I don't want somebody to get confused. Okay, if I had this as a product, an anti-halohydrin, and then that. This is one way of showing an anti-halohydrin addition. I can also say that my bromine's on a wedge and my OH is on a dash. And let's put my other things on the opposing things, right? So I can write these in two manners most of the time. So just do whichever one you want. Doesn't matter. Okay. Now we're going to talk about, if you have an epoxide, what can you do to it? So let's say I have an epoxide. And I'm reacting with H plus CH3OH. Okay, guys, pay attention. An acid catalyzed epoxide opening is going to attack more substituted carbon. So in parentheses, I'm gonna put, what the frick? In quotes, I'm gonna put like SN1 because you're attacking the more substituted carbon. If you're in a base catalyzed environment, you attack the less substituted carbon. And in this case, you can think of it like SN2. But what's going to be the same? Both of them will be anti-additions. Okay, so what is acid catalyzed? What is base catalyzed? If I have an H plus written, that means it's acid catalyzed. If I don't, it's base catalyzed. Usually, your acid catalyzed reactions will give you a weak nucleophile. So you can put that together, right? Weak plus acid equals attacking the more substituted carbon. Base catalyzed, usually they'll give you like a Grignard reagent, which we haven't talked about yet, or they'll give you like some other thing like that. And basic means you don't have an H plus, so you're basic. And so you're going to attack the less substituted carbon because you don't want steric hindrance. So if I did this reaction right here, let me just add something. Let's add this. If I did this reaction, what do I attack? I would attack with this, right? The first thing that happens though, let me redraw this. Let's do that. No chirality here. Let's do this. Okay, the first thing that happens is your alcohol gets protonated, and then you have your nucleophile, right? So CH3OH is going to attack this carbon here, break that off. And what do you end up with? End up with this, with your OCH3 attached, right? Pretending the workup occurred, and you'll have this. Now let's add some chirality. Since it has to be anti, right? Our alkoxy and our alcohol have to be anti, we're gonna show that. So I'll put this on a wedge, the CH3, and I'll put this on a dash. That means that my alcohol has to be on a wedge. And once again, you can do the opposite of this. You can put your OCH3 on a wedge and my methyl on a dash, and I can put my alcohol on a dash. Doesn't matter, the same thing. Well, not the same thing, but same answer. Okay, if I did a nucleophile that looks like this, let's use this nucleophile, negative carbon, which you'll see in the future looks like this, MGBR, Grignard reagent. This is a strong nucleophile, it's negatively charged, it's carbon, very nucleophilic. So this is gonna act like an SN2, where it attacks the less substituted carbon. It'll attack this, break off that bond, and what do you end up with? You end up with this. Wedge there in a dash alcohol, which means a wedge, this molecule. Okay, same thing, you can just swap the dashes and wedges, perfectly fine. Okay. Now, let's move on. We have like a couple more reactions to do. The first one is going to be a syn-diol addition. So a syn-diol just means that you have a product where you have two alcohols, right? They're diols and they're same side. They're both wedges, both dashes, both same side of the line. Why do we have this reaction? Because we have an anti-reaction, right? What is the anti-addition? Epoxide and react with H plus H2O. What does that do? H plus H2O, you protonate this, you have H2O, attack, carbon, and you get, what the hell? You're gonna get this. This would be OH and this would be OH. And to show stereochemistry, right, we did a backside attack, so one of them will be in the back, one will be in the front, or vice versa. This is anti-diol addition. So how do we do syn-diol? That's what we're looking for next. Syn-diol, there's two methods of doing it. So let's draw this. We'll do that. One is osmium tetroxide, OSO4, and I think there's like a H2O2 in this. On your double bond, you're going to put, or on a double bond carbons, each of them will get an alcohol. So this one will get an alcohol here, and this one will also get an alcohol there. Same side, both wedges are both dashes. And I'll put that thing right there. Or you can also use like a wedge now or something. Right? As long as my alcohols are the same side, that's all that matters. Another thing you can do, let's just do it, it's the same reaction, but just a different reagent. Let's do this, and we're going to react with KMnO4, but you have to specify cold and dilute, because if you don't do cold and dilute, you're assuming it's hot concentrated, which is a completely different reaction. So KMnO4, cold dilute, will do a syndiol addition. So I will get this. And you can fix your stereochemistry from here. Like, I'll just put that on a wedge and then my H on a wedge. So that's what syndiol is. So we know antidiol and syndiol. Do y'all see how we have all these reactions to do so many different versions of things? We have Markovnikov version of things, then anti-Markovnikov. We have syndiol, then we have antidiol. We have syn addition, anti-addition. We have all these things. Now, finally, right, for this chapter, we're going to talk about cleavage. Cleavage is important to know because this is the only reaction type you know which breaks carbon-carbon bonds. So if you ever get a question that looks like this, how do I go from a propane to an ethane? At some point, you must have had a cleavage reaction occur. Not initially, maybe not at the very end, but somewhere in the middle, a cleavage had to have occurred because that's the only way you can do this. So we're going to talk about it. We're going to talk about the methods of doing this. The first one is going to be ozonolysis. Okay, ozonolysis in your case is going to be what's known as a reductive cleavage or reducing cleavage, right? Whereas oxidative, I don't know what like the actual term for this one is. You can call it like strong cleavage or something, but oxidative cleavage is the one that, okay, no shit, but like it's the oxidizing one. And you don't know what this means, probably, but I'll tell you what it means. So let's say you have an alcohol. If you oxidize it by 1 degree, you can get an aldehyde. And if you oxidize it again, you can get a carboxylic acid. So if you're doing an ozonolysis right now, right? Ozonolysis can be oxidative, but they don't teach you that. So ozonolysis, you're only going to make carbonyls, okay? So carbonyls including aldehydes and ketones. So that just means something like that and something like that. That's it. 4 double bonds, okay? Just for double bonds. 4 double bonds only. Is a different thing when it comes to triple bonds. But oxidative cleavage, it can make carboxylic acids. But that's only if you have something at the end, right? So if something could be an aldehyde, it will be a carboxylic acid. If something is a ketone, it will be a ketone, right? So this one will make ketones and carboxylic acids. And of course, you can make CO2, which we'll talk about. The ozonolysis reagents are going to be O3. And this is the important part, right? You see zinc and DMS. You can use either or, right? You can either put zinc or DMS. Make sure you recognize what DMS is. It's dimethyl sulfide. So it could be shown as this, or they could do this, or they could do that. It's just dimethyl with the sulfur, right? For oxidative cleavage, you're taught KMnO4. And for this one, technically, you can say hot and concentrated, but it's not as important as saying cold and dilute as we do for the syndiol stuff that we just talked about. So you can either write KMnO4 or KMnO4 hot concentrated, but even if they don't write hot concentrated or you don't write hot concentrated, it's just kind of assumed that it's a hot and concentrated one. That's why like in your notes and stuff, they just write KMnO4. Okay, so we're gonna start with ozonolysis. Let's do this right here. And we're gonna react with ozone and zinc. If you do this is what I like to do. I like to just draw like a little cleavage right there and pull everything to the sides, okay? So you pull the left to the left and pull the right to the right. What does that do? Okay, literally pull it to the left and to the right. So we got this and that. All you're gonna do here is just add some O's in place of the double bond. So instead of connecting these, right, we broke them apart and we're sticking O's on both of them. That's literally your answer, right? You got a ketone here, acetone, and aldehyde. That's it, right? It's as simple as that. If I gave you, let's do that. And I think I'm gonna remove this right here. Okay, if I gave this to you and I did ozonolysis with DMS, right? Just cleave it in the middle, pull to the sides. Okay, the left side will look like this. And the right side will look like this. That's it, just put some O's on them. So that's your answer, right? The first one is this one. The second one, this one looks a little bit funny, but what do we really have? There's just H's here. This is called formaldehyde. You can just, that's it. See, nothing happens, like nothing crazy. This is the most simple thing you can do. And that's how ozonolysis works for double bonds, okay? I will mention this in the alkynes section, but when it comes to alkynes, the alkynes, you're not gonna make carbonyls. You're always gonna make carboxylic acids, even with ozonolysis. So just keep that distinction in mind. But for alkenes, it's very simple. Just pull them apart, stick some O's. All right. Now, let's say we're doing the other one, KMNO4. And I'll give you, start like right now like this, right? If you do KMNO4, do the same thing, right? Cleave it, pull to the left, pull to the right. What do we have? Damn it. We have this right here, okay? So if you have maxed out like R groups, meaning like, okay, I have 2 carbons here, that's it. I can't do anything else. I'll just put my O and that's it. What about for the right side? I know there's an H here, but I didn't even draw it, right? Because that's how irrelevant it is in this context. So this is what you're gonna do. You're gonna max out the space that you have. I can think of this as only 3 bonds, right? So I got an O here, and I'm missing a bond. I'm just gonna add an OH. I know there was an H there, but we turn it into an OH. It gets over oxidized. So that's what you're gonna get. If we had this, and we're reacting with KMNO4, cleave it there, and pull to the left, pull to the right. Left side looks like this, right side looks like that. Stick an O on the right one. This one's maxed out, right? I can't remove the carbons and say I want alcohol, like that's not gonna work. So this is it for the right side. For the left side, stick an O, add some more, and that's your product. You got acetic acid and this molecule here, right? So in your answer, you can just write both of them. And keep in mind, if you're doing a synthesis question, you can like choose. Like, what if you're doing a synthesis and you only want to continue with this one? You can say that in your synthesis. You can just say, both of these are my intermediates, but I'm continuing with this one. I'm going to do some LAH or something on that. You can do that. Just keep this. Is a good thing to like know that you can do. Okay. What about another situation? Let's say we had this and we cleaved it with KMNO4, right? We're still doing KMNO4 here. We already talked about what happens with ozonolysis. For KMNO4, okay, left side is done, ketone. Right side, now I have 2 empty spaces. So technically what happens initially is this, you get a formic acid, but this is going to over-oxidize, like something like this will occur, like where this becomes negative, forms a double bond. And what does that look like? It just looks like this. There's more to it. I'm just trying to simplify it, but you can scrap this, right? You end up making CO2, carbon dioxide. So if you have a terminal alkene, even terminal alkynes, just write CO2 for one of the products. And the other side, depending on what you get, you'll write that out. So on this side, we got a ketone and a carbon dioxide. Okay, we'll do one more thing. Those are like straight chains. What if we have a ring structure? Okay, we're gonna do this and that. And we're gonna say I'm reducing, doing an oxidative cleavage with KMNO4. This is where numbering is, I guess, kind of important. So we can do like 1, 2, 3, 4, 5, and 6. And then we also got carbon 7, and that's it, okay? So we're gonna cleave this, and we're also cleaving this. If you wanna keep it simple, you don't have to open it up. Like, you can just literally pull it up and pull it down here. So like I can write it like that. And this is perfectly acceptable. Just keep that in mind. Low-key, there was no need to number it, but I just did it anyways. So this is what we have right here. We have this. This is fine, once again. This is just like, you know, whether you open it up or not, it doesn't matter because it's just single bonds which can rotate. So this is a valid structure. So you have this, and you also have this, right? And let's finish it up. Let's finish it up. This becomes carboxylic acid. So do both of these, because we're doing KMNO4. And this one becomes CO2 because it's terminal and had 2 H's. That's what you would get for KMNO4. If you really wanted to open it up, which I'm telling you again, I'm emphasizing, you do not have to. If you really wanted to open it up, just number it out. And when you write your chain, make sure you're like putting the right numbers everywhere. I'm not even gonna do that because I don't want to confuse you. And if we did this question, but ozonolysis, which is the reductive thing, DMS, you know, same thing, just open it up like that. And this time it's done. You just put the O's, don't need to add anything else. And look, you got formaldehyde. Okay. Let's see. So that was it for alkene reactions as far as I'm aware. I don't think I missed anything. I mean, look, once again, I did skip some reactions like Simmons-Smith. I don't like that. But if there's something, like, just, you know, I told you to make a master sheet. That's gonna be useful to remember like all your reactions. But I did cover most of them, and I will continue to cover most of them. I think it's just alkenes where I'm skipping stuff. I don't know. But it's your job to figure out what I skipped, okay? Because I'm just going over some mechanisms and shortcuts and all that. So now we're going to go to alkyne reactions. This is like evidence of my video getting deleted. So let me go ahead and erase all this. It's very unfortunate, but you can ignore this, okay? So I'm telling you right now, I don't know what's going to happen. I think I'm going to cut the video right when I reach the part that my video like got murdered at. So if you see some weird cut and like the whole screen changes, that's why. So let's start with simple things right here. We got alkynes, and we're gonna draw this right here. By the way, okay, I don't know how deep it is, but don't do this, okay? This is supposed to be a linear molecule because it's, look, these are sp hybridized, right? So sp is 180 degrees. This is also sp, so it should be 180 degrees, meaning like a line. It pains my eyes to see something like this. I'm sure it pains your professor too, but I guess, you know, if you don't do it, well, that's whatever, but make sure you can like recognize how many carbons are in a molecule. This is 1, 2, 3, and 4. Okay, it's not 2 carbons because a triple bond is between these 2 carbons, which means a single bond is between these 2 carbons and that, right? So it's 4 carbons. So we have an alkyne. We can go to a straight chain alkane. We can go to a trans alkene, and we can go to a cis alkene. So when it comes to straight chain alkane, okay, before I even start, I want to let you know, if you know your alkene reactions, alkyne is much easier to understand because as far as I'm aware, like I think every single one of your alkyne reactions has an alkene reaction counterpart, and there's just less of them total. So I'll make those connections as we go, I think. So the first one, what do you think? Okay, I want you to think, what makes an alkene into an alkane? That's going to be the same reagent here, H2 with a catalyst, right? Platinum, palladium, nickel. Sometimes you'll see PDC, but the PD part is still the same. That's it. That's going to make it into an alkane. Now for trans alkene, this one you want to use what's called sodium and liquid ammonia. That just looks like this. I don't know how important it is to put the L. Like that is what you need to use. You don't want a solid ammonia, but like if you don't write the L, I don't think it's that deep. But if you remember extra steps in a reagent, just put all of them. There's no harm. It's only slightly harmful if you don't put it. So put this, right? This is going to give you a trans alkene. And lastly, we have Lindlar's catalyst. This is going to give you the cis alkene. So for your sake, like, it's perfectly acceptable to write Lindlar's catalyst if you're being asked to put in the reagents. But if you're given a question and they're asking you what is the product of this reaction, they might not write Lindlar's catalyst. They'll write out what Lindlar's catalyst actually is. So what is Lindlar's catalyst? Lindlar's catalyst will look like this. H2 palladium with barium sulfate. And there's also going to be something called quinoline. And I believe there's methanol present. What is quinoline? Highly doubt you need to know this, but quinoline looks like this. 2 benzenes, 1 has a nitrogen in it. But what I tell people is, like, if you see a barium, that should be a giveaway because this is the only reagent out of all your chapters, that has a barium in it. Or if you see quinoline, quinoline's also a dead giveaway. So now, you might be wondering, like, I don't know if I mentioned this already, but there's something called equivalency. So, like, if you get a molecule that looks like this, and they say, oh, I'm reacting with MCPBA, 1 equivalent. Once again, I'm sorry if I mentioned this already. I don't remember what I mentioned or didn't mention because of what happened. So if they give you this, you're saying there's only enough for 1 reaction to occur. So between the 2 double bonds, they're equivalent. So I'm just going to react with one of them. The other one stays as a double bond. If you're given this, by the way, this is just like a side tangent. If you're given that, the more reactive will be the tri-substituted alkene because there's more electron donating effects on it, making it more electron rich, and therefore it affects. And it's counterintuitive because tri-substituted is also more stable. You don't have to get into all that, okay? It's more stable, but it's also more reactive in this case. But that's what I'm talking about, right? 1 equivalent or 2 equivalents, that's what that means. So the reason I'm bringing this up is you might wonder, why can't I just say H2PT1 equivalent? Well, you tell me, if I do this, will I get a trans or cis alkene? The answer is you don't know. And in reality, this is a stupid reaction. Like, you're going to get a mixture of, like, your alkenes as well as alkanes and alkynes, and it's a whole mess. So it's a very unrealistic reaction. So you don't do that. Don't do that. Use what you're given, NaNH3 for the trans alkenes and Lindlar's catalyst for the cis alkenes. All right. Next, we're going to move on to halogenation. Another, like, identical thing, right? It's whenever I say things are identical to alkenes, like, they're either straight up identical or they're identical, but you just keep a double bond instead of making it single bond because you have an extra bond when it comes to triple bonds, right? So halogenation will look like this. And remember the intermediate for the double bonds? It's the same thing, except now you have, like, an extra bond. So you're going to bond to one of these bromines and break off that one. So you're going to get this intermediate. And then you have another Br minus come in, and it's going to attack one or the other side. It doesn't really matter because ultimately you end up with that. Now for this one, you need to fact check this. I don't really know, but I'm pretty sure I've seen somewhere that you get both trans and cis. Trans is more, like, logical to me, but just fact check this, right? I told you I'm not gonna tell you everything, so that's your job. So yeah, but same thing, right? You're gonna get 2 bromines or chlorines or iodines, like, on adjacent carbons. So it's just like the other one, right? The halogenation. And your intermediate's the same. Okay, now we got the HX, right? HX was the first alkene reaction we talked about. It's the same thing here. So let's say I have that, and I'm reacting with HBr. We'll just say 1 time, okay? 1 time. You either choose this one or this one to take the hydrogen, right? Option A or option B. Option B will take the hydrogen because your intermediate will look like this compared to this. They're both vinylic, but secondary is better than primary for cations. So we're going to go with this one. And then, right, this was H plus and Br minus. So this one took that, right? So Br minus comes here, it's going to attach itself, and you get this as your intermediate. Or this is your product for now. This is your product. But if I react this again with HBr, it's able to react again because it's just an alkene reaction. This time you just have a bromine on there. So what's going to happen, I have this with my bromine, and H plus and Br minus are present. Which one will take it, okay? Option A versus option B. Option A will give you this. And option B, meaning option B takes the H, right? If B takes the H, you're going to get that. Which one's better? This is secondary and this is primary. Now I know you're next to a bromine, which is electron withdrawing, which is bad for positive charges. But to your surprise, you can God damn it, I can't speak. You can resonate and you can get this. The resonance ability, kind of overpowers the electron withdrawing nature of it. So you can consider it as like an allylic secondary, which is amazing. So we're going to say that option A takes the H. Takes that, right? And your intermediate will be this, bromine, secondary carbocation. And then as you expect, you have a Br minus comes in over there. And your final product is a geminal dihalide. Gem dihalide. And as you probably are aware, you can make an alkyne with this. Yeah, type shit. If you look NaNH2 or something, or KOH. Okay, so this is like the Markovnikov version. And okay, hold on. Let me show you something. You see this right here? You see this? You might think, oh, why don't I just rearrange this from a vinylic to like a primary with resonance? You cannot rearrange when it comes to vinylic cations or even radicals or anions. Has something to do with the orbitals, okay? We're not going to get into all that, but you cannot rearrange, okay? So this one's actually Markovnikov, no rearrangement. You have to be on a normal single bonded carbon if you want to rearrange. Okay, so if this is Markovnikov, then we also have anti-Markovnikov. And the anti-Markovnikov will just be the other one, right? So you'll have this, and then you're going to do HBr. What do I mean by other one? The peroxide, right? Ruhr. We're not even going to do the whole mechanism here. It's the same thing, but with radicals this time. And so this is going to be anti-Markovnikov, which means the first time you do it, you're going to get that. And the second time you do it, you're going to get it on the same position. Hold up. What the hell? Okay. The second time you do it, you're going to get also there, right? So this is your product. What is this? 1,1-dibromopropane. That's your product. Okay. So another like identical thing to the alkenes, Let's move on. So if y'all remember from last time, from the alkenes, let me draw them again. For alkenes, we were able to do an alcohol addition to the Markovnikov position or an anti-Markovnikov, okay? So it's going to be the same here. It's going to be the same. What did we use? We used Hg and then OAC, right? And something. What did we use for this one? BH3 THF NaOH H2O2, okay? I made those certain like elements big on purpose. I'm gonna leave that there. If you get this right here and you want to do the alkene version of it, or the alkyne version, which would look like this, right? Right? Why do I say it's the alkyne version? Because in an alkene, you wouldn't have the double bond. You just get this. In an alkyne, you have the double bond because it's just extra bond. That's what I mean when I say these things. So if you want to do the the alkyne version, the Markovnikov addition of alcohol, you're going to use something with an Hg in it. In this case, it ends up being HgSO4, H2SO4, H2O, right? But the Hg is the same. The mercury one stays the same. What is the anti-Markovnikov version? First of all, it will look like this right here. It will look like that. And the reagent is going to be Cia 2BH, THF, H2O2, and OH. The only difference here is that in the alkenes, we say BH3. This time it's BHR2, right? I think I'm going to mention this when the video cuts, but the Cia thing is just carbons and hydrogens. You're being taught this, but this Cia thing does not have to be Cia, okay? Cia does not have to be Cia because it can be literally any R group. Do you guys know what Cia is? This is called cyamyl. And unless I'm stupid, I'm pretty sure it looks like this on both sides, right? So you're gonna have it on both sides. This is literally just carbons, hydrocarbons. It's an R group. And so that means it doesn't have to be that. It doesn't have to be Cia. So why am I telling you this? Because some people, when they're memorizing their reactions, they get so accustomed to this that if they see CH32BH, H2O2, NaOH, even though literally everything else is the same, the boron, the H2O2, the sodium hydroxide, they don't know what to do, and then they fail their exam and they cry and then they retake OChem and they never become doctors, right? Because they just didn't pay attention. Obviously, I'm over exaggerating. I'm scared someone's gonna take that literally, but I'm joking. I joke a lot. I need to shut up, bro. I just need to get to the point. Sorry guys. Hopefully you're watching this in 2x speed or 4x speed if you have premium. But Cia 2, no, nobody cares, right? Of course, recognize it because they could say that, and you don't know what Cia is. I just showed you it's carbons and hydrogens, but they can also write R2BH or something instead of R, like literally ethyl or methyl or propyl or something. So R2BH, H2O2, NaOH. What stays the same? BH. Also this, right? This is, what was the alkene version of this? It was BH3, THF, H2O2, NaOH. So it's literally identical, right? H2O2, NaOH, and the BH part. The only difference is that instead of H3, it's one H and R2. So what I'm trying to say here is that this is the reagent that will give you your anti-Markov-Nikov addition. So this is what you're going to end up initially with. But now, here's the very important part, okay? Your ultimate product will look like this. Your ultimate product here will be this, an aldehyde. So aldehyde and ketone. Why? If you have Dr. Pan's class, pay attention for real, because I had this mechanism show up on my exam. They were like, draw the mechanism of this thing that happened. And this thing that happened is called a tautomerism or tautomerization. So keto, enol, tautomerism. So this is called an enol, the big purple thing, because this is alkene, so ene, and this is alcohol, all, right? So enol. This is just ketone, right? So just keto. So you can go from a ketone to an enol and vice versa, or an aldehyde to an enol and vice versa. These are called tautomers of each other. They are not resonance structures. Instead, they're actually constitutional isomers. Count it up if you don't believe me. They're constitutional isomers. What a tautomer is, it's like a resonance structure with a shift in where your hydrogen is placed. So it's a mix of resonance and proton shifting. So as you can see, right, we had a hydrogen here, but we don't have it here. This carbon had 2 H's, now it has 3 H's. So that's what I'm talking about in terms of proton shifting. How does this work? Let's do keto to enol. So we have a ketone here, and we have, we're trying to get to an enol. So there's 2 ways to do it, right? There's base catalyzed and there's acid catalyzed. I'm only going to show you the base one because you can look up the acid one if you really care. So base catalyzed, base means hydroxide. You're going to deprotonate one of these carbons. So I'm going to deprotonate this carbon, take the hydrogen, make a negative charge. What do I get? O negative. What did this become? My OH took a hydrogen, so it becomes a water, okay? Water is in the background. Now I'm going to do resonance because I can. I'm going to do resonance here, form this enolate, big OChem 2 term. I'm going to form an enolate. Now what? My water that was floating around comes in. and my water will act as an acid this time. And it's going to give one of the protons to my oxygen. And ultimately, I end up with that, an enol. Now, I can also go backwards. I can go from an enol to a ketone. So I can go from this to that. What is the first step? Okay, I have a base. I'm going to steal my hydrogen, break that off, become O minus, do resonance, form this. What did this thing become? Water. Water is there, acting as acid. Give a proton to my carbon, and ultimately become ketone. And same thing with your aldehydes in this thing. Like, you can do the same thing there. It's just you have a H there. You have an H over here, right? Nobody cares. It's the same thing. So because you can do this, you're going to end up doing it. And these are in equilibrium, right? So I'm going to put a little arrow here. These are in equilibrium, but it doesn't mean they're equal. Like, there is an equilibrium, meaning that you can form some enol and some keto. But the one that ends up being made the most is your carbonyl, because the carbonyl is a more stable version. It's better to have a carbonyl than an enol. So what you can do is just assume a tautomerism is going to occur. So if I gave you this reaction, my product would not be this. My product would be the ketone. If I gave you this SiA2BH, this will give you the aldehyde, not the enol. And so the way I think about this is, when I'm doing my product, right, I still have 3 carbons, right? 1, 2, 3. 3 carbons. Where do I add my double bond carbon? It's either to carbon A or carbon B. Carbon A is more substituted, so it goes on carbon A, double bond O. What about for this one? 3 carbons, I either add it to here or here. Since it's the boron reagent, it's going to be anti-Markovnikov. I add it to the less substituted, double bond O goes here. That's my final product. If you want to add an H, you can. But this is my final product for the CA2BH. That's how this works. Sorry, I was checking my email. Okay, that's that's how this works. So, let me erase this now. Okay. And lastly, we have, I think, if I'm forgetting something, that's your job to figure out what I missed, because you're gonna have the master sheet, right, guys? So the last thing we can do is cleavage. So we'll do this for now. In this case, it does not matter what I have. Okay, when we had alkenes, if I used O3 DMS, or if I did KMNO4, I will get different products. What do we get for O3 DMS? We're gonna get this. That plus that. For KMNO4, what would I have gotten? This plus that. 2 carboxylic acids versus ozonolysis giving us 2 aldehydes. When it comes to alkynes, you can't form a carbonyl via the cleavage, as far as you're aware. So you're only going to form carboxylic acids, or even like CO2 if it gets over-oxidized. So you can use any reagent here. You can use KMNO4, or you can do O3. It doesn't matter. You can use KMNO4 or O3. And for O3, you know how we did ZN and DMS and stuff? Technically, you don't write ZN or DMS, you'd write H2O. That's because the ZN and the DMS are what play a role into the reductive aspect of the other one. That's why you don't get carboxylic acids. But if you do write zinc or dimethyl sulfide, like, it's just not going to do anything. So I don't think they're going to count off. But technically, you just put water because there's nothing else in the water. It's just water. And for both of these, your product will be cleavage and carboxylic acid. So you keep this carbon, right? The carbon's still there. But then you just put an OH on the other side. For this one, what do you have? You have this ethyl and this carbon, right? So we're going to have ethyl, carbon, and then carboxylic acid, right? Like that. That's it. That's all I'm gonna do. Same with the ozonolysis. I get the same thing. Now, if I had this, cleave it here, the left side will be right. The right side this time has a hydrogen. So you can either write this or you can just write CO2, like just say it fully oxidizes. Usually that's the case. If it's terminal, you'll write carbon dioxide. So that's what it's going to be. Okay. All right. Also, I'm pretty sure you can do the KMNO4 cold dilute here. But that's your job to figure out what it does. That's your job. I'm not going to tell you. But as far as I'm aware, we're done with the alkynes. Very light. And the reason I say this is because it's like, I don't think there was a single reaction here that we couldn't do with the alkenes. Of course, your reagents will differ a little bit, but the type of thing you're doing to the alkyne, you can do all of that to alkenes. So if you know your alkenes well, you can easily figure out your alkynes. It's not that hard. All right, now I like this chapter, alcohol synthesis, because alcohol synthesis is where you learn some stuff that's going to show up again on your MCAT, and it's also going to show up again in OChem too. Holy shit, I just forgot something. All right, alkyne, very, very big. I will actually refer to this again, but alkyne reactions. If you have a terminal alkyne, you can deprotonate it via NaNH2. This is a very strong base. This will deprotonate it, and you're going to get this acetylide ion. If you have an acetylide ion, think of this as a strong nucleophile that does SN2. Why is this important? If I want to add 3 carbons to this molecule, all I got to do is react this with the 3 carbon molecule. So 1, 2, 3. But remember, I have a nucleophile here. I do not have an electrophile here yet. To make an electrophile, I add a leaving group, so bromine. Then I can attack this carbon and kick off the leaving group, and I end up with, I added 1, 2, 3 carbons. And this might not seem like a big deal, but trust me, you can do so many things from here. For example, you can make this into an alkane. Whatever number of carbons it is, you can make it into an alkane, and then you can do anything. So this is very important when it comes to synthesis. I will talk about this again. Another thing, you can also make alkynes. I don't know if they talk about this that much, but you can make alkynes via NaNH2. So if I had this thing right here, and I do NaNH2, this will be such a strong base that I end up with this. This is called a vicinal dihalide because they're in the vicinity of each other, but they're not the same carbon. Alternatively, if I have this is called a geminal dihalide. If I have 2 halogens on the same carbon or one away from each other, as long as I have 2, and I do NaNH2, sodium amide, I can eliminate twice. Right, so like technically initially you get this, but then I eliminate again and I get my alkyne. So alkenes, knowing how to make those for sure, definitely know. Alkynes, maybe not as important, but if you know how to do it, it makes stuff easier. The more you know, the better, right? All right, now for real alcohol synthesis reactions. So for alcohol synthesis reactions, I'm trying to think, there's only like really 2. Yeah, okay, I remember now. Like if you do your thing, like if you look at your slides, there's like probably a lot of slides, but they're all the exact same thing. There's only like 3 unique things that you can do. So the first thing we're going to talk about is, in my opinion, the most important: Grignards. Grignard reagents. A Grignard reagent is just anything with MgX. So that could be MgBr, or it could be MgCl or something like that. First, let's talk about how do you make this. To make it, you need to have a leaving group first, like bromine, specifically bromine and chlorine iodine, right? And how do you do this? Let's say we have an ethane. You just Br2HV it, and you get 1 bromoethane, or just bromoethane. And then you react with magnesium in a solvent of ether. What that's going to do is it's going to displace your bromine. So you're going to actually be bonding magnesium to the carbon, and your bromine comes back. Now, what is the significance of this? In our bromoethane, our bromine is directly bonded to your oxygen, or you're directly bonded to your carbon. So this is a partial negative, this is partial positive. In this instance, I am an electrophile, so I can attack this carbon. But what does adding a magnesium do? Magnesium is partial positive. Sure, my bromine is partial negative, but my magnesium is partial positive relative to my carbon. So my carbon here is partial negative. That's very different. Right now, I'm a nucleophile. I'm a nucleophile, not an electrophile, because you're not partial positive anymore, but partial negative. So this concept is important to understand, because now we're going to talk about what you can do with this. So to start off, oh my God, I hate when this does this. What I do, if I have this right here, I personally, this is not literally what the case is, but what I tell everyone to do to make life easier is to scrap the MgBr and put a negative here. So when I have that, I think of it as I'm looking at this right here. Yes, I said this is a strong nucleophile, but it's also a strong base. Why am I saying this part? Because you cannot do a regular SN2 reaction. So do not ever do this reaction right here, where you're reacting with that. And I'm like, oh, I'm going to attack this and kick that off. In reality, what happens is something you can't even fathom. I'm not even going to tell you because it's annoying to explain. This will not work. This will not work. It's going to deprotonate your carbon and do some other BS. So you can't do that. What do I do instead with magnesium bromide? There's two things as of right now that you're going to have to know how to do. One is a carbonyl, or a carboxylic acid type molecule, right? We'll get into both of these. So this is one category. The other category will be your epoxides. Okay? My epoxides. These are just molecules with oxygen in them. If I have an oxygen, I can most likely do a Grignard reaction. Now, why? Understand this very well, because this is the basis of a lot of OChem 2 and on your MCAT 2. So this oxygen pulls the dipole moment upwards, making this carbon the electrophile. Okay, this is your electrophilic carbon. Now you're probably wondering, okay, I thought you just said it's a strong nucleophile and a strong base. Why would it attack as a nucleophile and not just deprotonate one of these hydrogens? The reason for this is because your ketones and your carboxylic acid derivatives, these are more electrophilic than acidic. Okay, sure, this is pretty acidic, because if you deprotonate it, what are you going to get? A resonance stabilized enolate. But this acts more as an electrophile than in acid. So because of that, you're going to treat your MgBr as a nucleophile. So if I have this, and I'm reacting with, hold on, give me 1 second. My brother's fucking alarm is going off. I had to turn it off. Okay. So if you have this and you're reacting with a carbonyl, nucleophile attacks electrophile. I'm attacking this, kicking that bond up. What do I get? I'm going to keep my carbonyl looking the same, right? Got my propane here. But now I just added a propyl group, 1, 2, 3. And that oxygen, instead of being double bonded oxygen, it's single bonded with a negative charge. Let's figure this out again. Let's explain why this happens. In this molecule, the only logical thing to break is a pi bond. I can't kick off a carbon or this carbon. That makes no sense. The only thing I can break is a pi bond, because what does it become? It just becomes electrons. So if I do attach something, if I do attach some carbons and I attack this carbon, I have to break something, obviously, because I already have 4 bonds. So I need to break something. The only thing I can break is this. That's why you're going to get this structure right here with a negative charge. Now, this negative charge is like, it's just there because that's what happens. That's like technically your intermediate, but ultimately you can assume an acidic workup and just protonate it. So your final product would look like that. Okay? All right, so that's just ketones and just aldehydes. Like, let's do an aldehyde real quick. If I had this aldehyde and I'm reacting with that, what do I do? Ethane. Make sure you count your carbons, okay? Even I mess that up sometimes. Ethane. Oh, by the way, sometimes they'll write H3O plus here. That's referring to your acidic workup, but even if they don't write it, just assume it's there. I'm going to attack this carbon, kick that bond up, and my product will look like this. Okay, let me highlight. This is what I just added. I still have a hydrogen present. I still have an H, I just didn't draw it in. But I still have it there. The H can't break off either. So I end up with this alcohol. Let's name this molecule, guys. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Doesn't matter. So we're going to go from the left to the right because we have a methyl here. So 1, 2, 3, 4, 5, 2 methyl, pent, and 3 ol. Damn it. Pent and 3 ol. That's what you're going to make. Okay. Now this is the one way you can do it. You also have other things that you can react with. This is called a carboxylic acid. Do not react with carboxylic acid. I'll tell you why afterwards. But you have derivatives of these, right? So this right here is called an ester. This is called an acid halide, in specific an acid chloride. This is acid bromide, acid iodide, right? You also have your amides. And there's some other things, but I think this is okay. You have, these are called thioesters. Anytime you see the name thio, that refers to sulfur. So a thiol is an alcohol with an S, so it looks like this. So a thioester is an ester, but with an S. So if you have these things, okay, you're going to react twice. Let's talk about why. If I have an acid chloride and I'm reacting with propane, magnesium bromide, propyl magnesium bromide, same thing. I'm going to write negative here. I want to attack this carbon, kick off that pi bond. I actually do have a leaving group here, okay? But technically, okay, if you want to think of it like that, you're free to do that. That's a simple answer. The simple answer is that. But in reality, what happens is you break your pi bond, because pi bonds will break before your leaving group leaves. So what am I going to get as an intermediate? Chlorine here, okay? I kicked off my pi bond, making O minus, and I have this. Why am I emphasizing this? Because I've seen this also show up as like a question for mechanism. You do need to understand this mechanism, right? This is called an intermediate. This is called a tetrahedral intermediate. Tetrahedral intermediate of this reaction. I've seen it before, so know this. What really happens is you're breaking your pi bond, not kicking off the chlorine. So now that we have this intermediate, what comes next? Your oxygen, if it has a negative charge, it's going to try to reform the double bond because it wants to form the double bond. It's more stable that way. So it's going to do it. And if it succeeds, it will succeed and kick off something. If it can't kick off something, it won't do it. So like in this case right here, when we had this, if you try to reform a double bond, there's no leaving group to kick off, so it's not going to occur. Therefore, it ends up just being stuck as an alcohol, right? But over here, if we have a leaving group, which in this case is a chlorine, I'm going to try to reform this double bond, and I'm going to actually kick this off. It's a concerted step, right? One step. So what ends up happening? I reform my double bond, and I have my propyl thing added. I drew this like this on purpose just to show you that this side is gone. But if you want to keep it nice and clean, we can draw it like this now, right? Like that. This is what I have after reacting with the acid chloride. Okay? What do you notice? This is a ketone. And what did we talk about before? Ketones and aldehydes react with Grignards. And you're going to do that. Because they just said you're reacting with this. We never specified, one equivalent, and they'll never specify for this because they want you to react twice. If you have this, it's in excess, unless specified otherwise, which I just said they're not going to do that. It's in excess, so you have more of this available. And since we have a carbonyl, which is very electrophilic, I'm going to attack it. So I will attack this, kick that up, and I will form this intermediate. Look, I just added this one, and I had that initially. As I mentioned, you're going to try to reform the double bond, but you can't because you can't kick anything off. So then you're stuck as a negative, you get protonated, become an alcohol, and this is your product. So let's take a step back. We started, let me erase all of this. We started as an acid chloride, so a derivative of a carboxylic acid. We started as this, and we reacted with that. And my product ended up having two of these in alcohol. So I had this, right? Alcohol, and I added 1, 2, 3, 1, 2, 3. Whoa. 1, 2, 3. I added two of them. So that's the shortcut. That's the shortcut. If you see this, if you see that, if you see this, if you see that, right? And you're reacting with a Grignard, just add your thing twice, okay? So all of these, this side will stay the same in terms of number of carbons. So you got one carbon, alcohol, and I'll add my thing twice. So 1, 2, 3, 1, 2, 3. All of these reacted with this will give you the same product because they all have the same ideology in that you can kick these things off. I know in an SN2 context or SN1, we don't consider this as a leaving group, but in these contexts, they are leaving groups because, for example, if this leaves, it becomes thioxide, and you can just protonate it, right, and make it a thiol, which is neutral. This one can become an alcohol, which is neutral, and so on. Okay, so we'll do this one more time. So let's say I have this versus that, and I'm reacting here with CH3MgBr, and over here I'm reacting with we're gonna do the mechanism again because you should know this. So the first one, CH3MgBr, it's just CH3 negative, which I can't even write out in line angle, so it's CH3 minus. This is going to attack our carbonyl carbon, kick up the pi bond, and give us the intermediate that, right, CH3. Since I have nothing to break off, my H3O plus will come in and protonate my oxygen, make alcohol. So this is my ultimate product. And you can just write it like that, right? Same thing. This is my product. Okay? Over here, what do I have? Scrap the magnesium bromide, put a negative on the carbon. This carbon, I'll just draw it again. 1, 2, 3, 4, right? This is going to attack the carbonyl carbon and kick the pi bond up. My intermediate will look like this. O minus, and my molecule, which is 1, 2, 3, 4, 5 carbons, is there. I'm going to try to reform my pi bond, and this time I can because the SR group can break off. And so that's exactly what's going to happen. And as of right now, my molecule will look like this. okay, where I added 5 carbons. Since this is a carbonyl, I'm going to react again with my Grignard. Attack this, kick that up, and what do I have? Hold up. So I just added this right here. So oh, wait, first of all I have a negative here, and I added 1, 2, 3, 4, 5. Oh no. 1, 2, 3, 4, 5. And then now, right, I can't kick anything off, so I protonate it, added H here, get rid of this negative charge, and that's my product. So my ultimate product is that. Okay, very nice. So once again, right, these are your carboxylic acid derivatives. You got ester. There's more coming your way in OChem 2, but these are some of them. Thioester, amide, acid halide, where X equals bromine, chlorine, iodine. Now, why did I say you can't do this right here? Okay, what did I say about Grignard reagents? They're strong bases. And yes, this is electrophilic, but there's no leaving group here. And so as a result, right, first of all, this is electrophilic, sure, and there's no leaving group, but this thing right here is very acidic. It's very acidic. If you deprotonate it, what do you get? Resonance stabilized carboxylate. So since that is very acidic, as you know, compared to just a carbon, which is pretty acidic but not as acidic, since this is very acidic, your Grignard will act as a base. And what is your product going to be? Your product will literally look like this. I don't know why I say literally like that. I'm just trying to make an emphasis right there. But this is what your product will look like. It's just going to be a deprotonated carboxylic acid. Like, that's not a real product that we want. So you can't do this. Why am I telling you this? They're not going to actually give this question to you. It's just that if you're doing a question and doing a synthesis and you're figuring out, do I want a carboxylic acid or aldehyde or ketone? Don't do this. Don't make a carboxylic acid and react with the Grignard, because you're not going to get what you want. Okay. And then, yeah, finally for Grignards, you can react with epoxides. So if I had this, this is kind of what I was talking about initially, like, I forgot, I think chapter 8. You can react with the Grignard. So we'll just do 3 carbons this time. First of all, strong nucleophile. Second, we're not in acidic conditions, which means we're basic conditions. So this is going to attack, right? And which one will it attack? It's going to attack the least substituted out of the options. So it's going to attack the right carbon. From the back, don't forget that, from the back, you're going to end up with an anti-product, and your OH is on most subbed carbon. So what do you get? Hold on. Okay, so you're gonna get, let's just do this on a dash, this on a wedge. Your carbon that you added will be on a dash, and that's 1, 2, 3. Does this make sense? I don't know why I ask y'all. It's not like I can hear your responses. So that's what you're gonna get. Once again, I said this already like 15 times in the past 10 seconds, but strong nucleophile, electrophilic carbons, anti-addition, because it's from the backside attack. And since you attack the least substituted carbon, because this is more like an SN2 than an SN1, this alcohol will be on the more substituted because you're attacking the least substituted and breaking this off onto the more substituted carbon. Okay. Now, I know this is not chiral, but it doesn't matter. I'm just showing you, right? Let's just make this an ethyl then. Let's go ahead and make an ethyl. All right, you still get that product. Okay. Cool. So now we're gonna get into our reducing agents. So we have NaBH4. This will, one second, reducing agents. NaBH4. We also have lithium aluminum hydride, which you can sometimes see written as LaH. And lastly, we have rainy nickel, which technically is actually H2 rainy nickel. So hydrogen, rainy nickel. So all of these are reducing agents. They can reduce. So for example, what I showed you all this at the beginning, but I showed it the opposite direction. If you want to reduce your carboxylic acid by 1 degree, you can make an alcohol. So you can make, no, hold on. You can make a aldehyde, right? An aldehyde. If you reduce it again, you get an alcohol. So these are like different degrees of reduction. So depending on the type of reducing agent you have, it can reduce some things and not other things. Or it can reduce everything. What else can reducing mean? If you have a double bond, you can reduce it into single bonds, right? Removing the double bond means you're reducing it. Adding double or triple bond means you're oxidizing it. So of course, we know how to do this on its own, but you might be able to reduce all of these along with your double and triple bonds. Who knows? We'll find out right now. So NaBH4 will only reduce these three things: ketones, aldehydes, and acid chlorides or acid halides. So all of these, if you react with NaBH4, they're all going to become that. And then, sorry, actually, let me just draw separately for the ketone. Your ketone will look like this, a secondary alcohol, and your other two will look like that. I just drew them differently just to show you the different methods, but they're all going to look like that. And the way this works, you can think of it like Grignard. You're going to have a hydride ion, and it's going to attack your carbon and do all the stuff we talked about, right? There might be a slight difference, but for the most part, it's the same. And so because of that, what I want you to remember is that this chlorine thing, or whatever you have in the other cases, it breaks off. So it leaves, right? Your chlorine's floating around, and then it does something ultimately. But your actual product is going to focus on these two carbons and the oxygen becoming alcohol. Does that make sense? I'll tell you why I mentioned that thing in a second. But let's draw this again. Acid chlorides. You're probably not going to see acid halides. You're going to see these two primarily, but still no acid chlorides for the future. Now, lithium, NaBH4 is like mild. We call it a mild reducing agent because it can't reduce that much. We have more things that we want to reduce. Lithium aluminum hydride, on the other hand, is a strong or a stronger reducing agent. So this can reduce everything NaBH4 can do, right? So our ketones, aldehydes, and acid chlorides. But this can go ahead and reduce our carboxylic acids and the derivatives. So we have carboxylic acid, ester, thioester, and all the other things, amides. If you reduce them, okay, just remember, I said that this thing leaves. It breaks off because of how the mechanism works. You have an H minus, kick that up, reform the pi bond, kick this off, right? Because of that, if I gave you a question that looked like this, people wonder what's going to happen here. NaBH4, what is your product going to be? Your product will look like this. Because nothing happened. NaBH4 can't reduce this. But if I did LaH, lithium aluminum hydride, remember, this thing breaks off. It just breaks off from this carbon though. It doesn't break off from the entire molecule because it's connected via a ring. So I would draw it like this. I have my alcohol up here, and I'll draw my ring the same, just opened up. And my oxygen here, which technically is minus, but through workup becomes OH. So that's what my product would look like. And of course I have my H's here. Okay, keep that in mind. That's what's happening to your oxygen and your sulfur when you're doing these reactions. Now, if I have a double bond that I want to reduce, along with my ketones and aldehydes, of course, I can do two reactions. I can react with like LAH, and then next I can do H2PD or PT. That would give me this product. That would give me this. But if I want to do it in one step, in one reagent, I can use H2 rainy nickel. Rainy nickel is a very strong catalyst. So not only does it reduce everything that NABH4 and LAH do, it also reduces double and triple bonds. Okay? So once again, if I had this and I wanted to reduce it by one reagent, H2 rainy nickel. That's my product. Now, here's the thing though, okay? You gotta be careful. I think this is a common knowledge by this point, but for Organic Chemistry 1, never touch a benzene. You'll learn why in the future. But a benzene is very stable. You might have heard the term aromatic. Aromatic is a whole like set of stuff occurring in the molecule that stabilizes it more than you expect. It's not just resonance, there's way more occurring in that molecule. Therefore, you don't want to touch it. I mean, if you did want to reduce it, it takes something that you can't even fathom. So even though H2 rainy nickel is very strong, it's just not strong enough. It's not strong enough to reduce this. And so you would still have this product. You'd still have a benzene ring. Okay? And that's simple for you to understand because you don't have to worry about benzenes. You don't have to worry about attacking these or attaching anything on. That's a whole separate chapter in OChem 2. So keep this in mind. If I had this molecule and I wanted to reduce that, my product with H2 rainy nickel would look like this. So I only reduce this double bond because it's not in an aromatic ring. And I reduce this alcohol because it's just a ketone or aldehyde that became an alcohol. Okay? And this applies to anything. If I had this and I reacted HBr, I'm not going to just take one of these double bonds out. No, this would just be no reaction. There's a different way to add bromines to your rings, but you're not going to do that right now. All right. So we covered all of this stuff. I think that's everything in alcohol synthesis. Yeah, it's a lot of stuff that we talked about, but once again, do your master sheet and it will make life much easier. So now we're gonna do some synthesis, okay? If you don't know your reactions, your reagents, but at least you know what's possible, that will help a lot, right? So you can actually do these questions I'm going to show you and try to do them yourself. Like just pause the video and try to do them yourself. At least write out the reaction. For example, like, you know, I'm just making this up. Write this out. And then something, right? Even if you don't remember the reagents, see if it's a real reaction. Of course, these are real reactions, but they're not like going to maybe occur here, but that's what I'm saying. What you might think, okay, let me just do like this or something. Now, that's not a real reaction. You might not know that, but if you look at your choices, your options based on all the reactions you're given, you'll know it's not possible. So start with that, and then ultimately you can go ahead and fill in the reagents. But anyways, I'm going to show you like how I do this. But before we begin, if you're my student, you've heard this a billion times, but big emphasis here. Carbon-carbon bond forming reactions are very important because there's not too many of them, but that's a lot of synthesis. Like if you look at this question right here, we have 6 carbons, and now we have 12 carbons. So if you ever see something like that, you should automatically be thinking about your reactions that form carbon-to-carbon bonds. And there are 2 main ones, okay? You did learn a couple others. For example, this thing right here. This is technically a carbon-carbon bond forming reaction, but I don't count that because that's not going to get you anywhere. What can get you somewhere is if you can extend the carbon chain, okay? So we already talked about both of them, and I'm going to bring them up again. The first one is your acetylide ion. What is an acetylide ion? It's your carbon negative bond on a terminal alkyne. So if, like, look, for example, if I wanted to do, if I had this right here, and I wanted to make that, all I gotta do, deprotonate this with NaNH2, okay? And how many carbons am I trying to add? 1, 2, 3, 4. Just introduce an electrophile that has 4 carbons. So 1, 2, 3, 4. How do I make an electrophile? Add a leaving group. Chlorine, bromine, iodine, something like that. And this is what happens. It attacks this, kicks it off, and makes that. Okay, so this is one thing you can do. And keep in mind, yes, this involves a triple bond. And you might think, like, triple bonds are not there in a lot of my synthesis questions, so I don't need to do it unless there's a triple bond. It doesn't matter. This is a triple bond, but you can reduce it into a double bond, right? If you use NaNH3, or if you do Lindlar's catalyst, you can even make it into an alkane with H2PT. So even if your product doesn't have a triple bond, it doesn't mean you didn't do a triple bond. You could very well do a triple bond reaction. So keep this in mind, okay? So this is one option. The other option is what we just talked about right before this. Not the reducing agents, but your Grignard reagents. Sorry, my Apple Pencil's tip fell off. So Grignards. Grignards are more likely to show up because Grignard is like a very important topic. Like, it just shows up a lot. Like, I think this guy got a Nobel Peace Prize for it. By the way, if you find out a new way to do carbon-carbon bond forming reactions, you're going to get a Nobel Peace Prize. Don't ask Dr. Thompson because she disagrees, but I'm telling you, you will get one. So, Grignard reagents, why? If we have this, and I have this molecule has 3 carbons. If I did my reaction, what do I end up with? This product has 5 carbons. And I bonded this carbon to that carbon. That's called a carbon-carbon bond forming reaction, right? Same with the other one. When you had this, and I bonded to like that, I bonded this carbon to that carbon. These are the only 2 ways you know how to do it while actually extending your chain. And as I mentioned, it's super important because if you get a reaction, a synthesis question, and your product has more carbons than your starting material, you should automatically think about one or both of those occurring. Not necessarily both occurring in the synthesis, but I'm saying that you should think of both of them as a possibility to occur. So before we even do the synthesis, I'm going to give you a little fun one. I'm going to give you a little fun question. Can you go from a propane to a butane? Figure this out on your own and then we'll begin. So what we're going to do here, I want to essentially bond this carbon to another carbon. So that means that I either make this the nucleophile or the electrophile. Now, I can do triple bond potentially, but I don't want to do triple bond. I mean, I can, right? I could. We'll do both ways. The first thing to do, it's a little bit more annoying, it just takes more steps, but I can do Br2HV and get myself this. If I do it again, I'll get this. Remember what I said, if you have 2 bromines on the same carbon or just one away from each other, you can do NaNH2 and form a triple bond. Okay? Then from here, I can do NaNH2 again to deprotonate it. And I just want to add one carbon. So since I have a nucleophile, I just got to make a one carbon electrophile. What is my one carbon electrophile? CH3 leaving group. So CH3 iodine or something. Okay. And that is going to give me this 4 carbon molecule alkyne. How do I go from here to my alkane? H2 nickel. So that's one way I can do it. What's another way I can do it? We already said that there's 2 possibilities. One is alkyne and one is Grignard. So we're going to do Grignard. So for this one, I can either make this into the Grignard reagent or I can make it the, carbonyl. Now, for carbonyls, right, if you wanted to make that into a carbonyl, you would have to either make this into an alkyne and then a carbonyl. So like if you had this, right, we had this to begin with, you can do the reaction, the Ca2BH, H2O2, right? All that, you can make this into an aldehyde, and then you can react with CH3MGBr. That's another thing you can do. And attack this, form an alcohol. What would that give you? This right here. You're all following along, right? You make an alcohol. Then what do? Okay, I need to make this into a double bond so I can ultimately get rid of it. H2SO4. H2SO4 will give me this, and I can just do H2PT. And there's a third way I can think of, right? A third way is making this your Grignard. So we're actually going to do that because I want to show you all the possibilities. There's not usually, sometimes there's only one way to do a synthesis, but there's not always just one way. So how would I do this? This was my initial preferred method, which I realize is not the only method now, right? You can brominate it, Br2HV, make this, and ultimately I want a bromine here. So how can I do that? I would have to form a double bond first. So I would use LDA here. Why am I using LDA? Because it doesn't matter. I would still get a double bond where I want it to be. If I use NaOH, a professor might make the argument that you do SN2. So with LDA, you're comfortably able to do E2. And there's no Zaitsev or Hoffman here. It's just that. Then, to add the bromine to the end, I use HBr peroxide, right? Just Ruhr. And then, my bromine gets attached over here. Then to make this my Grignard, magnesium in ether. And finally, not finally, but you can react with a 1 carbon carbonyl. So I'm gonna draw my carbonyl here, and just 1 carbon. So the rest are just H's. What is that gonna do? Right? And same thing from here. You can dehydrate it to give you technically this because you have a rearrangement. And finally, H2PT. So as you can see, I just did 3 methods. That's not always going to be the case. Sometimes there is literally only one method to do it. But you can think about this. Like, I want you to think, can I make this into a nucleophile, or does it have to be the electrophile? Which one's easier to do? All of that stuff. So now let's begin with my actual things. This molecule right here, I can work backwards, I can work forwards. It just depends on what you're given. So I want to work backwards here because I see this, right? I'm just telling you how I logic these things out. I see this right here, an epoxide, okay? I know how to make an epoxide. The epoxide has to come from a double bond. So I'm going to say that. My very previous step was a double bond because if I just use MCPBA, that will give me my epoxide. Okay, now I'm kind of thinking, like, how can I go from there to there? Obviously not one step, but I formed a carbon-carbon bond. So I essentially added 2 rings to each other, right? I added 2 rings to each other. And I see that I formed a double bond, and I know that if I do a Grignard reaction, right? If you do a Grignard reaction, you're going to make an alcohol, and I know that I can form an alcohol into a double bond, right? So I'm thinking about all those things. I only know they occur because I know my reactions well. So I will go ahead and work forward at this point. I want to add this ring. How many carbons? It's just 6 carbon cyclohexane. I want to add that carbon, and I'm going to treat that as the Grignard reagent because this is my electrophile. So I will make a Grignard reagent out of a cyclohexane and do that. And what I'm really looking at is a negative on this carbon that will attack that, kick this off. And in like at this point, I have this. Let me draw it the other way, 1 second. I have this, and my alcohol is there. Right, this is carbon 1, carbon 2, carbon 3. It's carbon 1, carbon 2, carbon 3. I just drew it differently. So I made my alcohol, and now I need to go from alcohol to a double bond. H2SO4, dehydration. And it's good. It's going to make my Zaitsev product because it's tetrasubstituted alkene. So that's how I do this question. Okay, the next one. The next one, I have to figure this out, right? There's like a bunch of stuff occurring here. First, I extended my chain to like 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5. So my straight chain is still 5 carbons, but I added a carbon here and a bromine there. So at this point in time, I have no clue what occurred, but I'm going to think. I either did a Alkyne reaction or I did the Grignard. The logical answer here would not be Alkyne. Like I would not deprotonate this because deprotonating it would only extend my chain. As you might have noticed when it comes to Grignards, sometimes you extend your chain, but sometimes you just branch off. So that's what I'm going to think of. So I'm going to try something out. I'm going to try to make this into a aldehyde just because I'm trying to form a bond here, right? If I wanted, I meant to say ketone. I want to form a bond here. That's where I'm branching out. So that means that this thing needs to become my, you can call it the Grignard substrate. I want to make it my carbonyl. And I want to make it on the Markovnikov position because this is the carbon that's going to be attacked. So what do I do for that? HgSO4, H2SO4, H2O. After tautomerism, what will that give me? It'll give me this. Okay. Now I just have to add 1 carbon. So to add 1 carbon, you just do a 1 carbon Grignard reagent. So CH3 MgBr with H3O plus. Right now I will get this. And actually, I'm going to draw the alcohol downwards. So as you can see, I have this thing drawn now. I have this, right? This thing in blue. I made that chain. Now, what do I do? So I know that this bromine can only have come from a double bond, and it had to have been anti-Markovnikov. I know I can make a double bond because I have an OH. So I'm going to do that. H2SO4, I'm going to make my double bond. So I can get rid of it because I don't need that OH. It's not part of my final product. I made this double bond and I want to add my bromine to the least substituted position. So what do I do? HBr and Ruhr. Simple as that. What about this one? So what I'm seeing right now is I have an ethoxy group that I added to this carbon, okay? But how do I get that ethoxy group? It looks like I did an SN2 or an SN1 because this is the only, or technically like there's many ways to do this, but what I'm thinking right now is that I must have SN2 attacked a bromine. So let's work backwards for this one. Let's say that right before this, I had that, and I just reacted with NaOCH2CH3, okay? Then how do I go from here to here? I can't just Br2 HV this because that would go over here. So the only way I know how to make a bromine on that position is it had to have come from a double bond. And it would have to have been anti-Markovnikov, so HBr Ruhr. So the intermediate before this would look like that. And this is simple now, right? All I gotta do is just Br2 HV. That would give me this, and then I can do LDA specifically because I want to form a Hoffman double bond, and I made that. Okay, so let's do another one. This one looks like, I had a ring and it's opened up, so I'm automatically thinking about a cleavage occurring. This is a perfect opportunity to cleave because you have a double bond there. So that's what we're going to do because there's nothing else you can do. So we're going to cleave this. And you have two options with a double bond. You can either do ozonolysis or you can do the oxidative cleavage. I would not do oxidative cleavage. That's just me thinking right now. I'm just thinking, right? I'm not telling you a reason why. I'm just thinking it's generally better that we do ozonolysis because that's what we end up using. And it makes it easier when we're trying to form bonds, right? So you can try it out though. Try out oxidative cleavage, see what happens. But that's one thing I'm noticing, right? The next thing I'm noticing, this is 6 carbons. How many carbons is this? 1, 2, 3, 4, 5, 6, 7, and 8 carbons. So I did have some carbon-carbon bond forming reaction occurring. So the first step I'm going to do is just cleavage, okay? Just O3 DMS. And I'm going to get this, right? So you're going to separate the two sides like that. And I'll just write it nice and neat. So we have this and we have that. Now I need to add carbons to the left and the right. So I'm only adding 1 carbon each. So I can react this with CH3 MgBr, H3O plus. Now this is why I'm saying that I need to do reductive cleavage rather than oxidative, because I'm only adding 1. Do you see how this chain only added 1 carbon and 1 carbon? Like, if I did a carboxylic acid derivative, it would have more. It would have like a branch out like that. That's why I said that. So I know I'm going to do this, and it's obviously an excess, so it's going to react with both of these. And what do I get? Alcohol here and alcohol there. So this chain is this chain. Next, I'm going to dehydrate both of them. So H2SO4. Dehydrate and dehydrate. And finally, I think I actually forgot to mention this in the beginning, but I think you all also know. Like, the first thing I noticed, I didn't even say it, that's how second nature it was. But when I see this, it's epoxide again. Had to come from a double bond. So that's why I was trying to make a double bond, if that wasn't clear. But I'm trying to make double bonds, and ultimately I can do MCPBA or some sort of peroxy acid like that. Okay. Let's do a couple more. So for this one, I see that I need to extend my chain, right? I have a benzene, and it ultimately ends up as a benzene with like 3 carbons added. And so, okay, can I do this one? I cannot, because if I did this, this would be the electrophile. And as I mentioned, you do not touch the benzene. So you cannot attack this benzene and kick that off. That's not going to work. So the only thing you're left with is a Grignard. And you can make this into a Grignard, right? You can make it into a Grignard. And so that's what you're going to do. You're going to react with Mg ether and make that into a Grignard. So in other words, the benzene nucleophile, and I want to add 3 carbons. Okay, how can I do that? So I need to make sure that I'm reacting with a carbonyl compound, because Grignard reagents are very basic. Remember, they're not going to work with your typical electrophiles. So I'm going to make a 3 carbon, carbonyl, and I'm just going to make the aldehyde at the end because I want to make sure I bond to this carbon and not the other one. Otherwise, it's going to look like a branch. So I will do that. And what do I get? I get that, and my alcohol will be up here. Now, I see that I have an anti-diol that was made. To do anti-diol, I need to have an epoxide and react this thing with H plus H2O or just H2O. Because one side will get the OH and the other side will also get OH. It's the same thing. And it's a epoxide attack, so it's going to make an anti, right? So I need to make a double bond first. And I'm going to do H2SO4. That will give me that. There's nowhere else the double bond will go, right? Then I can make my epoxide. So MCPBA. And I will get this. I don't care about the stereochemistry anymore. So I'm going to make that. And finally, okay, if I react with H plus H2O, as I said, it doesn't matter. Okay, if you do H plus H2O, you will be attacking this carbon, just letting you know. But you'd break this off, right? So you'd have H2O here, attacking that, breaking this off, and you ultimately end up with the anti-diol, as indicated by a dash and wedge. That's how we do that one. I think this is our last one. Okay, this is our last one. This one was really tricky, but what do I see here? I see that, so I'm going to highlight this in purple, right? This purple is just this right here. So all I added was alcohol and this benzene. Now you can do the long way or the short way. You're able to do this a very long way, but I see that I made an alcohol, and you know, we have a whole chapter. Chapter 10 is literally called alcohol synthesis. So I want you to think about those reactions. Okay. You can of course do like your NABH4 and that stuff, but there's no ketone or aldehyde or anything. What else do we have? We have epoxides. Epoxides can make alcohols. Ketones make alcohols, but I just said, right, we don't have a ketone or anything available. So the only thing that makes sense is your epoxide. And you'll see what happens. But what I can anticipate is that there was a double bond here. I can anticipate that. So let me write this out really quick. The reason I can anticipate this is because if I form an epoxide, then all I have to do is attack this carbon, break this off. And that will literally move the oxygen here, right? Like, not literally move it, but it's on this carbon, right? This carbon has methyl-methyl alcohol. This carbon has methyl-methyl and potential alcohol. So all I gotta do is attack the less substituted carbon, break off that oxygen, and I'll be done. Okay, does that make sense? So we're gonna work like semi-backwards. So we know we need to make a alkene, and then we need to make an epoxide. So we'll do MCPBA to give us that. And ultimately to go here, just make a reagent out of this, like a nucleophile. So I'm adding this, right? So it needs to be a methyl benzene, and then MGBr, because I'm trying to add carbons, don't forget that. So it needs to be MGBr. And definitely don't do acidic environment, just do this reagent, don't do H+. Because if you do, you don't want to attack the more substituted position, you want to attack the less substituted position. So this attacks this, breaks that off, you ultimately get this molecule. Okay, so how do I go from the starting to this one? I'm going to brominate it. And I can just use any strong acid or strong base, because I'm not going to worry about SN2 occurring here because I'm on a tertiary position. So NaOH works just fine, and that will give us that. All right, hopefully you got a lot of practice in. If not, there's always more available with the drop boxes. So now number 7, right, is very interesting. These are called cleavage puzzles. We do these in PLTL, but they're not like, I didn't expect these to be showing up in your class, but I've seen a lot of people crying about their quizzes, wondering how do you do this? And so I'll prepare y'all just in case. This question, you can just go ahead and read it. You can pause the video. I'm not going to read it out loud. But we're trying to figure out the starting material, right? So you have some starting material, and if you do ozonolysis, you get all of these three products that they show us. And so there's a few things I can think about. Number one, I know I have 3 double bonds because it says that I react with 3 equivalents of our Br2CCl4, right? Br2CCl4, this is one of our alkene reactions. So if I react 3 times with it, that means I must have had 3 double bonds, okay? Another way I know I had 3 double bonds, if you do any cleavage, how many carbonyls do you get? You get 2 per cleavage, right? Because you get one of these and one of that. So how many carbonyls do I have? I have 1, 2, 3, 4, 5, and 6. So 6 divided by 2 is 3. That's another confirmation that I have 3 double bonds. What else? I know I have a ring structure, potentially. I'll tell you why. There's like a better way to determine, but do you see this right here? I have 3 carbonyls in one compound. Like, that must mean I had a ring that opened up. That's what it looks like. But look at this formula right here, C9H12. There's a formula for degrees of unsaturation. A degree of unsaturation can either be a double bond, it could be a triple bond, or it could be a ring. So double bonds are 1 degree of unsaturation, rings are 1 degree, and triple bonds are 2 degrees. So we can calculate how many degrees of unsaturation using this formula. It's 2 times the number of carbons plus 2 minus hydrogen. There's more to this formula, but this is all you need to know for now. If we, all of that over 2. If you do this, you get 20 minus 12 over 2, which is 4. So 3 of those are double bonds. The last one has to be a ring structure. Can't be a triple bond, because that's 2 degrees. And it can't be a double bond, because we only have 3 double bonds. So I had a ring structure. Okay. So this one, right, you can try working it out now. Like, what I would do is try to figure out which of these carbonyls came from each other. Like, you know, did this one come from this one? Like, did I have a structure that looked like, you know, hold on. Did I have a structure that looked like that? If I cleave this, I would get that. Okay, you can think about it like that. Did this one come from that? Or did this one come from that? You gotta try to figure this out. But what I will do first is figure out what the ring was, right? Your ring got opened up, and so it's gonna be within this molecule. These two make absolutely no sense because that's gonna be a 3, that's literally this, right? Cyclopropene. I highly doubt that that's the case. Technically it could work, but that's like a very weird molecule to do. So I'm going to think that these two came together. Okay? I'm going to think that these two came together. How many carbons away are these centers? 1, 2, 3, 4. There's 4 carbons in that molecule. So I'm going to draw a square. I'm going to draw a double bond. Right? The reason I only count from center to center is because if I have a molecule that looks like this, and I cleave this, and I open it up, it's going to look like this. I did this wrong, actually. Wait, 1 second. I think I misnumbered the carbons, but it doesn't matter. But what you can see here is that I have a very long chain. And it doesn't mean that this carbon was bonded to this one. All I'm saying is that these two are bonded. They cyclize into like a hexane. And then you had this chain separate. So that's why I want to count from carbonyl carbon to carbonyl carbon. In this case, 1, 2, 3, 4, that's a cyclobutane. So I'm putting those together, okay? And I'm going to number this before I even put the double bond. I'm going to number this as 1, 2, 3, and 4. The double bond was between carbons 1 and 4 because those are what form the carbonyls, right? So I'm going to put a double bond here. Okay, carbon 1 also is bonded to this on the left side, right? This circle was separate from the ring. Because if it was within the ring, it would be bonded in the middle to like both carbon 4 and carbon 1. But since it's only bonded to carbon 1, it's going to be only bonded to carbon 1 in your cyclobutane. So I'm going to draw an ethyl here, 1, 2, like that. Now carbon 3 also has a carbonyl there. But that carbonyl came from its own thing, right? It's not like within the ring. It must have had some sort of like chain that got cleaved there. That's exactly what happened because it's a ketone, right? Do you see how this is 2 carbons here? So if I were to cleave it, it would make a ketone, whereas carbon 4 has an aldehyde. And look at this. Carbon 4 has an H, which is going to make an aldehyde if you cleave it. So it makes sense that carbon 3 is going to be bonded to some chain that got cleaved. And right now, we have how many carbons? 1, 2, and then the ring is 4, right? So that's 6 carbons. I'm missing 3 carbons. So I'm just going to assume that my carbon chain at number 3 is 3 carbons long. So 1, 2, 3. We'll confirm this. I'm just assuming, right? I'm just guessing because it just makes life easier. So right now we have 1 double bond, okay? I'm going to circle these because these came from the same double bond. We're trying to figure out the rest. Another thing I noticed is this formaldehyde. The only way you can have a formaldehyde is if you had, right, you can have a long ass chain, but if it's terminal, the end will have 2 hydrogens. And that's the only way you can have a carbonyl there. So that means that my formaldehyde either came from here or from here. So we'll just keep those as options. I'll put like a dash here and a dash over there because both of those are viable. So now I want to figure out, okay, where could this have come from? Oh, by the way, I forgot this right here, double bond. Where could that 2 carbon dialdehyde have come from? Let's think about it. You had to have had a cleavage that looked like this. So 2 carbons bonded to something, cleave and cleave. Something like that. If you do that, look at this. These 2 carbons are within the same molecule and they both form their own carbonyl. Does that make sense? So you want to look for a place that you can do this. If you had your double bond here from the previous thing, where else can you form a double bond such that you'll have a 2 carbon molecule? It's not possible. So if I form my double bond here, look at this. 1 carbon, cleave here, cleave here. That will give me exactly what I need, right? So that's how I know my double bond is there. And so this is our product ultimately. I'll draw it again, nice and pretty. It's gonna look like this. That's our final product with this double bond. Okay, we're gonna do one more cleavage puzzle because I'm now realizing how more likely these are to show up on your exam than I thought, like more than even these mechanisms. So let's do this, right? The first thing I notice is that it says C9H10. And I also see that it says that we're going to get a propyl cyclohexane if we react with H2PT. So that just means all of our double and triple bonds go away. So this is our base molecule. I'll go ahead and draw my propyl cyclohexane. Cyclohexane with a propane on it, right? That's my base molecule. And I just got to figure out where do I put my double and triple bonds and how many are there? Okay, also the C9H10, let's figure out degrees of unsaturation. So we're going to do 2 times the number of carbons, right? So 2C plus 2 minus H over 2. This is going to equal 2 times 9 plus 2 minus 10 over 2. This is 20 minus 10 over 2, which is 5. So I have 5 degrees of unsaturation. And what is this composed of? 1 is for sure a ring because that's what our base molecule looks like. That means the other 4 degrees of unsaturation were a combination of double and triple bonds, or maybe all triple or maybe all double bonds. That's what you got to figure out. So what else can I see here? I see that we're doing ozonolysis, or you can see it right here. We're doing ozonolysis, and how many C double bond O molecules do we get? 1, 2, 3, 4, 5, and 6. Regardless of what type of cleavage I'm doing, every cleavage will give you 2 C double bond O molecules, right? If I'm cleaving this, that's 2 components, right? And I can do whatever I want to them. So that means that if we have 6 of these, just divide it by 2 and you get 3, okay? So I have 3 cleavages, meaning I had 3 double and or triple bonds present. But if I just put 3 double bonds, that's 4 degrees of unsaturation. I'm missing something. So if I just like do some like mental math, I can know that I have 1 triple bond and 2 double bonds. But I know this answer is not sufficient for a lot of you. So I will tell you another way to confirm. Look at what you're given in your products. You're doing ozonolysis And ozonolysis for alkenes will only give you aldehydes and ketones for now, right? So these are both aldehydes in this case. The only time you're doing ozonolysis and you can get a carboxylic acid like we have over here is if you're doing an alkyne. So like if you cleave this, the left side would look like that, which is a carboxylic acid with a methyl. The right side would end up being CO2 actually. Or if you want to like underoxidize it, you get this, right, with an H. But in both cases, I'm getting carboxylic acids because it's an alkyne. So that means that out of all of my products I'm given, 2 of them are carboxylic acids, and 2 carboxylic acids came from 1 cleavage. So 1 cleavage gave 2 carboxylic acids, meaning that we cleaved a triple bond to make both of these carboxylic acids. So I know that I have 1 triple bond and the rest of them, right? These are all aldehydes. Actually, they're all aldehydes, yeah. Aldehydes are ketones, whatever. But aldehydes, those gave us our, what did they give us? They came from our double bonds. And that there's 4 of them, right? So 4 divided by 2 is 2. So I know I have 2 double bonds and 1 triple bond. And let's add this up. A ring and a double bond, they all equal 1 degree of unsaturation. And a triple bond equals 2, right? So I'm adding 1 plus 2 plus 2, which is 5. So it matches out. It all adds up. Okay, so now let's figure this out. The first thing I'm going to start with is our triple bonds because there's only 1 triple bond, right? And they have the carboxylic acid. This is very easy because our molecule is mainly a ring, right? We have this thing right here. And I know for a fact that my triple bond had to have been inside, not inside, it had to have been on the propyl substituent because you're never going to have a triple bond inside of a ring. Okay, for now, you might, but like not right now, definitely not right now. Okay, so your triple bond must have come from outside, but we're not going to go by assumptions. We're going to look at our products. I'm looking at this carboxylic acid. It's detached from every single other molecule, and it only has a methyl, right? So to make this, I have to have a alkyne that looks like this, because the right side, right, it has a methyl here. The methyl refers to this methyl, and then it's done, and that gives us a carboxylic acid. So I know that in this propyl substituent, the only place it can go is here, okay? Because once again, this makes no sense because, I mean, look, your carbon is maxed out. This carbon can't have 5 bonds. And this will make no sense because if we did this, we should have either that or a CO2. And I don't have this present. The smallest carboxylic acid I have present is with the methyl, right? So I can't be a terminal alkyne. I have to be internal, but just enough to give us 1 methyl. So it would look like this. So if I cleave this, look, I'm bonded to a methyl. So I have a methyl and then COOH, right? That's what it's going to look like. So that's what it looks like. I'm going to just make it like linear now. So we figured out the triple bond. Okay, so I'm going to highlight this one because we figured it out. This came from the right side of this cleavage. It came from the right side of that cleavage. And I'm going to continue on with this molecule because if I know that the right side of this triple bond gave this one, I also know that the left side gave rise to this carboxylic acid. And that's right here, right? So this carbon that I'm marking in red is this carbon that I'm marking in red. And we're going to continue this on. I'm going to call this carbon 1. And let's go right to left. Carbon 1 is bonded to carbon 2, which is bonded to carbon 3 before we reach a cleavage. Okay, so let's do the same thing. You see how the direction is going like this? Carbon 1, carbon 2, carbon 3. You can follow that along in this ring. This is carbon 1, go down, carbon 2, and go up, carbon 3. Boom, it ends, right? I have a double bond at this point. How do I do that? By simply adding an alkene, right? So I'll get a cleavage here and a cleavage there, and that will give us my double bond O and my COOH on that side, okay? Following along, I hope you are. So we figured out that part. And now let's go down from carbon 2. Carbon 2 is also bonded to carbon 4, and it ends before you reach a cleavage. So we're going to do that too. At carbon 2, I'm going to go down, call this carbon 4, and boom, it ends, okay? It cleaved. If you have a double bond over here, that means I had a double bond right there, an alkene. So this actually ended up being my answer because I have both of my double bonds and my triple bond figured out. So that's it. But we're going to confirm this now. We're going to confirm it by looking at the last molecule and one more thing, right? But this molecule is the only one we didn't talk about yet. Let's look at it. it has 2 carbonyls, and what is the numbering over here? We'll just call it 8, 9, and 10, right? So it's a 3 carbon molecule. Let's look at this side. We didn't look at this side over here. Let's call this carbon 8, 9, and 10, right? That's exactly our molecule because it cleaves. It cleaves, right? 1, 2, 3, 4, like that. Right? 8, 9, and 10. It cleaves enough to separate it from the rest of the molecule. So this entire thing is gone, goes to the left side, and you get this molecule right here. Okay? So I hope this made sense, but worst comes to worst, at least figure out how many degrees of unsaturation you have, as well as figure out how many double and triple bonds you have or rings, and just plug and chug. You know, if you have time, hopefully that works out, but I think it should be pretty like understandable. It is a little bit confusing, I agree with you, but it is doable as well. Okay, so now let's use this molecule and let's just cleave the whole thing. I know we kind of already did this, but we're just gonna do it again because I just want to prove that this is correct. So we'll cleave this right here, pull it to the right side, okay? That thing is going to give us a 2 carbon, or like a methyl on a carboxylic acid, which is this, okay? So we figured that out. We'll put it to the side. And then let's pull the alkyne to the left. And this whole thing will be like our R group, but the ending will be a carboxylic acid, right? So we'll just call this carbon 1, carbon 2, carbon 3, and we'll call this carbon 4. So if you do this, you're doing the orange cleavage and you're doing this and that. So what does this look like? Get rid of this and get rid of that. And I'm gonna write out the chain first, right? 1, 2, 3, and 4. 1, 2, 3, and 4. What is carbon 1 going to become? It's on an alkyne, so we're gonna add a COOH right there, or just an OOH, right? Carbon 2 is nothing, it's just a carbon bond to carbons. Carbon 3 has double bond, so it becomes double bond O. Carbon 4 is also double bond, so it becomes double bond O. Okay, so we figured that out. We did that. Now finally, we're doing the other side that we didn't do yet. We'll call this carbon 6, 7, and 8. Okay, carbon 6, 7, and 8. Let's pull these to the left side. This will give us what? Let's write out carbon 6, 7, 8. Carbon 6, 7, and 8. What is carbon 6 bonded to? It's a double bond, so this is gonna form our aldehyde. Carbon 8 is bonded to a double bond, right? So it's gonna be aldehyde. Carbon 7 is nothing, it's just a carbon. And look at this. We have these 3 molecules, the gray, the pink, purple thing, and the orange. This entirely matches up, right? The gray molecule is this. The pink one is this. And the orange one is this. I just like flipped them. But that's how we do this. That's how we confirm that we're correct. Let's move on. We're almost done. But common ranking. So I don't think there's that much new ranking. Literally just these 2 things that you can see are the only things I can think about. The rest of your ranking will be stuff that you covered in the past, like SN2 reactivity, SN1 reactivity. Really good resource is OChemRank.com. Just look up OChemRank online. It will either take you to a website directly, or it will take you to a school page that has a link for it. But definitely do this because the professors made this, and so sometimes they'll copy questions directly from there, and it just has a lot of practice for all the different topics. So I would highly suggest that. So the first type of ranking you could get is alcohol acidity. Now, in my opinion, this isn't really new because it's very similar to just regular acidity. Remember areo, mnemonic? Areo is atom, right? If you're comparing a carbon versus oxygen, which one is more acidic? You look at the stability of the conjugate base. The oxygen is more stable because via atom, we're looking at the most electronegative. And then like if you had, let's say like NH2 and pH2, then if they're in the same group, you look at which one's lower. So this one would be more acidic, right? So that's like the only difference. Like you actually have to determine about the atom. When it comes to alcohol acidity, the A is the same. So then you look at resonance, inductive effects, and orbital does not matter. You look at resonance and inductive effects. So over here, conjugate base, right? O minus. I'm going to draw all the conjugate bases. and that. So the first one, what can it do? This one can resonate, and I'm going to go ahead and draw the resonance structure. Okay, looks like it can only resonate one time, unless I did something wrong, but I didn't. So we'll just call this, able to resonate. And what is this? It's a secondary alcohol, secondary allylic. I'm going to put a 1 time here, because you might have more resonance. I don't know. Why is it secondary? Whenever you have an alcohol, you look at the carbon your alcohol is bonded to. Whatever type of carbon that is, that's the type of alcohol you have. So since this carbon is secondary, your alcohol is secondary. All right, so we have that. This one is a tertiary alcohol with no resonance. And just keep in mind, we're dealing with a negative charge here, so you do not want tertiary. Primary is way better. Over here, we have a secondary, no resonance. And I also see this NO2 nitro group. This is an electron withdrawing group. So we'll just keep that in the background. And then over here, this is a secondary, no resonance. And finally, what do we have? One resonance structure that can look like this, and a second one that can look like that. Okay, so this is secondary, allylic, more resonance. So since this one has, these two have resonance, so I'm just going to go by which one has more resonance. This one has the most, that's number 1. This one has the second, so it's number 2. Now between the rest of them, tertiary is the worst, so this will be number 5. Now the last ones, this is just secondary, and this is secondary with electron withdrawing group. Electron withdrawing group is good for negative charges because you're withdrawing electron density from something very negative. So this one will be better. Right? This will be number 3, and this will be number 4. It just has like a bunch of methyls and stuff. The next one is ranked by rate of reaction with HBr. I've seen HBr, but they could use anything. There's many other options they could use, because the essence of this question is, what is the intermediate? The intermediate is a carbocation formation, right? So one of the first reactions we talked about, H plus, Br minus, you take it, form a carbocation, potentially rearrange. So you're ranking by carbocation stability, including rearrangement is possible. So that's what I'm going to do. The very first one, I'm going to write it out as a carbocation, and I'm going to rearrange it. Okay, so I'm going to say tertiary if rearrange. This one, which one is going to react between these two double bonds? It's going to be the first one I circled, this one, because you get a better intermediate. Why? It's a benzylic, whereas this one would be just tertiary. Tertiary is good, but it's not able to resonate. So this one is better. And don't forget, you will never touch these for OChem 1. So just leave that there. It's a whole benzene ring. So this one is secondary benzylic. What is this one, if I draw it? Tertiary, no need to rearrange. And lastly, I'm not going to redraw this, but I'm going to go ahead and put my carbocation right here. Versus, I forgot the double bond here actually, but the carbocation will be right there. So let's go ahead and do this, right? This is tertiary. This is tertiary. This one's just tertiary. And then this one's tertiary with rearrangement. So the number 1, of course, would be this one. Well, not primary. I meant number 1 because it's able to resonate, benzylic. Now, out of the rest of them, this one is tertiary, but that's if you can rearrange. What is better, tertiary with rearrangement or just tertiary without rearrangement? Without rearrangement is better because it takes less energy, right? If you have to rearrange, it takes some energy, so you end up being slower if you have to rearrange. So I know that this one is less than this one. I'm just going to keep that in mind, okay? Now, as for the other ones, there's a lot going on. But what I noticed, first of all, is that there's a lot of electron donating groups here. Like we have all of these carbons, and NH2, OCH2. There's a lot of electron donation. So off the bat, I know that both of these are going to be better than both of these, making this one number 4 and this one number 5, because between the 4 and 5, the one that has to rearrange is less stable. It's it's like less fast, or it's slower because it takes energy. This is number 4. Now, the only difference I see between the remaining two, other than the fact this is O and this is NH2, technically NH2 is a stronger electron donating group. You don't have to know that though. What you do need to know is fluorine versus bromine. Fluorine is a stronger electron withdrawing group than bromine, which means that it's very, very bad for positive charges compared to bromine. So since the top right molecule, right, everything else is identical, since this one has a less strong electron withdrawing group, the effects are not as much as this one. So this will be ranked number 2 and this will be ranked number 3. That's how it goes. Okay. Oh, okay, one more time. I want to emphasize, don't touch the benzene. I've seen in a ranking question where they'll include this. They'll just give you some molecule that looks like that, and they'll add this to the ranking. This would automatically be number 5 because there is no reaction with HBr. There is no double bond to react with, so just keep an eye out for that. Okay, so we're done. We're done with all of the chapter 8, 9, and 10 stuff. Yeah, I covered a lot of stuff. I think it took like 3 or 4 hours. And so now I want to talk about just these things right here. Like, you know, this is some like fundamental stuff. Maybe it'll show up like 1 or 2 questions, but definitely want to talk about it in case you forgot. Because I remember when I was studying for my final, I was like scared of Neumanns and Fishers. So we'll briefly go over them, as well as determining isomer types. So Neumann, don't forget, right? A Neumann will look like this. We'll have A, B, D, E, F, and G. If I want to draw this in line angle format, I can do 2 ways. So number 1 is looking at my molecule from the left side. So this is my front carbon, right? It's going up. My planar thing is going up. So I'm going to draw a carbon with something going up. That would be my A, okay? So this is my front carbon, and I'm bonded to my back carbon over here that you can't see, right? For my back carbon, I have this G going down. So down here, my G will be like that. Now, if I'm looking at it from the left side, yeah, that's the left side. If I'm looking at it from the left side, first, I'm going to point something towards me. If I point something towards me and I look at it from the left side, it's going to be on the right side. So that something that's towards me is our wedge. And since it's on the right side from this direction, all of my wedges will be the ones pointing to the right. So for my front carbon, my B is on the right side. That means my wedge is a B. And the back carbon, my E is on the right. So it's going to be on a wedge. And then whatever we have left will be on a dash. So this will be D, and the other one will be F. Okay, so that's one way you can do it. If I wanted to draw it from this side, then I'm going to put my front carbon, let's do it down like this, and my back carbon over here. My front carbon has the A going up, so it's going to go up like this. I'm bonded here, so A. And then my back carbon has the G going down, so G like that. From the right side, something pointing towards me will be facing to the left, and something pointing away from me will be towards the right. Just try to visualize it with like a pen or something. But since my wedges are on the left, that's what I'm going to do, right? And my Neumann, if I have something on the left, like D, for example, that's on a wedge. And then the back carbon, it's going to be F. And then the rest will be dash, right? So B and E. Now, how do you go from a line angle to a Neumann? Let's use the same example right here, but we're going to do it from the different direction. We're going to go from this direction. We're going to look at it from this side. So what I do is I look at my front carbon. This is my front carbon. This is my back carbon. My front carbon, the planar component is going downwards. So I can either draw it like this or I can draw it like that. Since it's going downwards, I'm going to go with this one right here. So that's what I'm going to do. I'm going to draw this like that. And the back will just go up. So my front carbon, what's going down? The G. In my back carbon, what's going up? A. Now I'm looking at it from the right side. From the right point of view, my wedges will point left. So if I have a wedge, like E for example, that's pointing left. So I'm going to have an E over here, and then F on the other side. What about the back? B on the left because it's on a wedge, and then D on the right. So that's how you do this. Now, how do we go from this to fissure? Fissure projection will look like that. The shortcut, okay, if you have just 2 carbons and you want to do a fissure, the shortcut is to put everything on the front the same how it is. So do you see how my front carbon has a G going down, has a F going to the right, and an E going to the left? I keep that the same. But for what's on the back, I'm going to flip it. So of course, I'll keep my A here. But do you see how we have B and D? So B is on the left and L is on the right. Whoa, B is on the left and D is on the right. I'm going to flip it. So I'm going to put B on the right and D on the left. This will always be correct. That's like a shortcut. If you want to take a longer route, or if you're like scared, check chirality. Okay, check chirality of both of these and match it up with your line angle structures. This is not a good example because these are arbitrary letters. But when you do check chirality, keep in mind that your horizontals are wedges. Okay, so if you have an H on a horizontal, you're going to have to flip whatever chirality you get. Like let's say you got priority 1, priority 2, priority 3, and you're going counterclockwise. Since this is on a wedge, you got to flip it, and that would give you like R, for example. But that's just like, I'm just telling you. Okay. So that's just like, yeah, pretty much it. Now lastly, how to determine isomer types. So the very first thing you do, okay, what is an isomer? An isomer has to have the same formula. The moment you switch one thing, you're no longer the same thing, right? If you have C5H9 and the other one is C5H8, they're not isomers. They're very different. They're completely different molecules. And so your answer would be none, right? So you want to make sure that you have the same formula. So step one is check formula. If the formula is not the same, your answer will be N, neither, nothing. Let's say step 1 checks out, you have the same formula. What is step 2? Step 2 is check connectivities. So if I have this and I have this, they both have the same formula, right? They're both C3H7Br. They're both like that. But what's the difference? In the first molecule, I have this carbon that has 3 H's and this carbon has 3 H's, okay? But on the right molecule, this has 3 H's, but none of my other carbons have 3 H's. This one has 2 and this one has 2. So my like thing was CH3 bonded to CHBr bonded to CH3. What did it become? It became CH3. Okay, this checks out. But this bonded to CH2, which is bonded to CH2Br, right? So like this is different than that, and this is different than that. So it's not the same, okay? It's not the same connections, but since our formula is the identical, we're gonna call this constitutional isomers. Constitutional or structural isomers. Now let's say that step 1 and step 2 match out. Then this is where you check chirality. If you have a full flip in chirality, and as long as you're not meso, you're going to be an enantiomer. So for example, if you have RRS and you become SSR, that's an enantiomer. If you have partial flip, meaning that something flipped but not everything flipped, you will be diastereomer. So for example, RR becomes SR, that's diastereomer. And if you have no flip or just achiral to begin with, then you're going to be identical. So if you have R becoming R, that's going to be identical. Or if you just have something, right, like this, like straight up achiral, This is achiral, so they're the same molecule, considering that 1 and 2 check out. Okay? So those are like your steps. That's like your little flow chart. That's what you want to check for. So we're going to work through each of these and use these rules, right? So let's go ahead and get rid of this stuff. Or just leave it on the side. So the first molecule, right, this is, it should be obvious. Like these are obviously, they're either not the same thing at all, or they're going to be constitutional just because you can visually tell, right? But let's count. You have 1, 2, 3, 4, 5, and 6. C6. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. H14. What is this one? 1, 2, 3, 4, 5, and 6 carbons. So C6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. H14. So they have this same formula, just oriented in like branch differently. So they're going to be constitutional isomers. What about this next one? This next one, what I would do is you can rotate, right? If you can rotate, that's good. I think a lot of people know what I'm talking about, but it's like confusing to show. So what I'm going to do is just draw them in line angle structure. So I'm going to draw it like this. So we got CH3 here. And then for the back, we're going to have and then we have our CH3 and H2. Okay. And then for the other molecule, I'm going to go ahead and draw it like this. You might notice that this front carbon is not chiral. That's good to know, keep in mind, right? So I have these two molecules. They're definitely like bonded the same. Like I have a carbon that's bonded to NH2, CH3, and H, which is bonded to a carbon that's bonded to H, H, and CH3. That's identical. So they're either going to be identical or enantiomers. They can't be diastereomers because we only have one chiral carbon, right? This is not chiral and this is not chiral because they have two H's. So we're just looking at the N, NH2 and stuff, right? So let's determine the priority here. Priority 1 will be the nitrogen. Priority 2 will be this, and priority 3 will be that. This looks like it's going in a clockwise fashion, but since our H is on a wedge, this would be counterclockwise. So this would be S. What about this? Priority 1 is here. Priority 2 is there. Priority 3 is here. This looks like clockwise, but since our H is on a dash, we keep it clockwise, right? So these are going to be R, and the other one is S. That means they're enantiomers. Okay, so this is an enantiomer. Let's move on. These molecules, this is a cyclohexane, so is the other one. Don't forget how your chairs look. If you're going down, you're on a dash. If you're going up, you're on a wedge. So we have a methyl going down. 1, 2, 3. So 1, 2, 3. On the 3 position, we also have a bromine going down. You can look at chirality or you can just look at it visually, right? What's the difference? My methyl changed, my bromine stayed the same. So since only one thing flipped, that means that like it's a partial flip, right? It's this situation here. So I'm gonna have diastereomers. Okay, let's move on. This one, we can go ahead and figure out chirality. Let's just make sure, right? This carbon is bonded to iodine, CH3 and C2H5. This carbon is also bonded to iodine, CH3 and C2H5. This carbon is bonded to Br, H, and CH3, and this carbon is bonded to Br, H, and CH3. So yeah, step 1 and step 2 check out. Now we can figure out chirality. This one, priority 1, priority 2, priority 3. That looks like it's going clockwise, but since our H is on a wedge, this is going to be counterclockwise or S. Okay, what about the other one? We got iodine's priority 1. Then we got priority 2 here and priority 3. So this looks like it's going clockwise again, but since our lowest priority, which is our methyl, is on a wedge, this is going to be S. Over here, iodine's priority 1, this is priority 2, and that's priority 3. This is going to be R, because our methyl's on a wedge. And lastly, we have 1, 2, 3, which also is going to be R. So we got to flip it. So over here, we went from SS to RR. That is a full flip, making this enantiomers. Okay, this one you can rotate or you can just figure out chirality. It's up to you. I'm going to figure out chirality. So when you have a H on a line, you can like rotate and figure out chirality, or you can do like my little method. So since you have an H on a line, you kind of like can't figure out chirality directly. So what I would do is redraw this and swap the location of your dash substitution with the H. So we'll do that, right? We'll get COOH, we get methyl, that NH2, CH3, and we're gonna put our H over here, okay? Let's figure out the chirality of this thing. So priority 1 is this, priority 2 is that, priority 3 is here. So this molecule, right, this is going to look counterclockwise. It looks S. Since this is S, the original one was R, so we'll do that. Over here, same thing. Our H is on the line, it's on the plane, so we're gonna swap the location of this with the thing on the dash. And what do we get? Put our methyl here. We'll get our NH2 there and our H over there. So rank this priority 1, 2, 3. That also looks like it's going counterclockwise. Since we made this swap, whatever we get over here, we're gonna flip it, and that will be our chirality over here. So we went from R to R. Everything was the same. So this is going to be an identical molecule. Finally, or actually not finally, we have 2 more. This one right here, I'm just telling you off the bat, like you can count it up and stuff, but these are going to be actual tautomers of each other. This is some OChem 2 stuff, but this is kind of like the keto-enol stuff, except this is called an imine, and this is called an enamine. But these are tautomers, right? And if you remember what I said about tautomers, tautomers are just constitutional isomers. They're not just resonance, right? You have resonance and you're moving your proton around. So since that's the case, these are just going to be constitutional. And once again, you can count up the atoms if you want and see, but I'm telling you I'm correct. Now lastly, if you know, you know. This is an if you know, you know question. I'm not going to elaborate. If you know, you know. But do this question real quick. 5, 4, 3, 2, 1. You're wrong. It's not diastereomers. It's not diastereomers. Yes, we went from a wedge dash to a dash dash. But are these carbons chiral? No, they're not. They're not chiral. This is CH3 and this is CH3. So are all of them. So because of that, all I'm looking at is this, right? These are not chiral. So they're going to be identical molecules. Or you can call them conformers, like conformational. But in this case, they're going to be called identical. Okay? So we are officially done. I'm very paranoid. I feel like I forgot something. I don't know what I forgot though, and I probably won't remember until after this is posted. So I hope y'all learned something. I hope y'all watched this video. I hope y'all make this thing, by the way. But if you have any questions, please leave them in the comments below, and I will respond. If you need help with a certain question that maybe I didn't cover, you can also send a comment, or you can potentially get my number from somebody. Somebody must have it. A lot of people have my number for some reason, so you can do that. And I will try to remember to include my sheets for this, but please make your own. I don't care about you copying mine. That's not the point. It's just that you're going to learn better if you make your own. And once again, mine might have small mistakes, so I don't want you to get the wrong information. But other than that, I hope you had a good time. And yeah, I don't know what to do anymore. I'm so tired. I'll see you on the next one next semester for OChem 2.